Hello there and welcome to Science for Sleep, where curiosity gets comfortable, the lights stay low and science takes its time. Tonight we're heading far beyond the familiar stars of our night sky, past the galaxies we can see with ordinary telescopes, and back toward a period when the universe was still very young. Our subject is an object with a name that sounds simple, dramatic, and perhaps slightly suspicious: the dark star. At first, the phrase seems easy enough to understand. A dark star must be a star that does not shine. Perhaps it is an old star that has gone out, a black hole wearing a less alarming name, or a large ball made entirely from dark matter. All three guesses are reasonable. All three are also wrong, which is a promising way to begin. A dark star, at least in the scientific idea we're exploring tonight, would not necessarily be dark to our eyes. It could be extremely bright. It would not be a black hole, although it might eventually help create one, and it would not be made mainly from dark matter. Most of its substance would be ordinary hydrogen and helium, the same basic ingredients expected in the earlier stars. The unusual part would be the source of its energy. Instead of beginning its life by relying on nuclear fusion in the usual way, it could be supported by heat released through interactions involving dark matter. That is a rather strange arrangement. It is a little like discovering a house built from bricks and timber, then learning that its central heating is powered by something no one has ever held, seen directly, or stored in a sensible cupboard. Dark matter is one of the most useful mysteries in modern physics. Scientists use the term for an unseen form of matter, whose gravity helps explain how galaxies rotate, how galaxy clusters hold together, and how large structures formed across the universe. We cannot look through a telescope and take a normal photograph of dark matter. It does not appear to absorb, reflect, or emit light in the usual way. We know it is there because visible objects move as though extra mass is present. Imagine walking into a room and seeing the curtains pulled sideways, papers sliding across a desk, and a lampshade wobbling steadily. You cannot see the air moving, but the behaviour of everything else makes the draft difficult to deny. Dark matter is not simply a cosmic breeze, of course, but the comparison gives us the basic idea. We notice its influence before we understand its nature. Now place that invisible material in the early universe, when the first dense clouds of hydrogen and helium were gathering under gravity. Ordinary matter was falling inward. Dark matter was already helping to shape the gravitational wells where that collapse could happen. Under certain proposed conditions, the concentration of dark matter near the centre could become high enough for its particles to release energy. If those particles were able to annihilate with one another, some of that energy could be trapped in the surrounding gas and converted into heat. That heat could change the story of the forming star. Normally, a cloud contracts because gravity pulls it inward. As it shrinks, it grows hotter and denser. Eventually, if the centre becomes hot enough, hydrogen nuclei begin to fuse, and a conventional star switches on. Fusion then supplies pressure that pushes outward, balancing the inward pull of gravity. The star settles into a long argument between collapse and expansion, with neither side quite winning for most of its life. A dark star would enter that argument differently. Dark matter heating could begin before ordinary fusion became the main power source. The extra heat would resist further collapse, allowing the object to remain larger, cooler at the surface, and more spread out than a standard first-generation star of similar mass. It could continue collecting gas while dark matter supplied enough energy to support it. So, despite the name, we are not talking about a dead star. We are talking about a proposed early stage of stellar life. It would be active, growing, and luminous, but its internal energy budget would be unusual. The star would still contain familiar matter. Gravity would still pull inward. Gas pressure would still push outward. Light would still try to escape through the outer layers. The surprising guest would be dark matter, contributing very little of the total mass while potentially supplying a great deal of the power. And that leads to a question worth carrying with us tonight. When you hear the words dark star, What do you picture? Do you imagine a black sphere blocking the stars behind it? A faint object hiding between galaxies? A giant sun with its light switched off? Or perhaps something stranger, glowing brightly while being powered by matter that remains invisible? You can also tell me where you are listening from tonight. Maybe you are under a clear sky with a few stars visible through the window. Maybe clouds have covered everything. Maybe the nearest view of space is a tiny weather icon on your phone, insisting that rain is once again a strong possibility. Wherever you are, it is worth remembering that the light reaching Earth from distant objects began its journey long before any of us were here to receive it. The farther away we look, the farther back in time we see. Light does not travel instantly. Even moonlight takes a little over a second to reach us. Sunlight takes several minutes. Light from nearby stars takes years. Light from distant galaxies may have travelled for billions of years. A telescope aimed deep into space is therefore not only looking across distance, it is looking into the past. That is why the idea of dark stars is connected so closely with the earliest periods of cosmic history. If these objects existed, they would have formed when the universe was young, before generations of stars had filled space with heavier elements. We would not expect one to be sitting quietly beyond Pluto, waiting for someone to notice it. We would search for its ancient light in extremely distant regions, stretched and weakened by the expansion of the universe. This makes dark stars difficult to study. They are hypothetical objects from a remote era, powered by particles whose identity remains unknown, observed, if they are observed at all, through light that has crossed an enormous distance. Science has chosen a puzzle with several missing pieces and placed it at the edge of the observable universe. Apparently, ordinary crosswords were not enough. Still, the idea is not random. It grew from calculations about how the first stars might form inside dense concentrations of dark matter. Researchers asked what would happen if dark matter particles could annihilate and deposit energy into collapsing primordial gas. They found that, under the right conditions, this heating might become strong enough to slow the collapse and create a new kind of stellar phase. The proposal depends on the nature of dark matter, and that nature is not settled. One frequently studied possibility involves particles that are their own antiparticles. When two such particles meet, they could annihilate, converting their mass into other particles and energy. Some of that energy might escape, but some could remain inside a dense forming star and heat it. This does not mean dark matter would burn like coal or fuse like hydrogen. It would not gather around a tiny fireplace in the centre, despite the obvious advantages for illustration. The energy would be released through particle interactions distributed through regions where the dark matter density was high enough. The heating rate would depend on how much dark matter was present, how concentrated it became, what kind of particles it consisted of, and how often they interacted. Those details matter because a dark star is not a confirmed category of object in the way that red giants, white dwarfs, and neutron stars are. It is a theoretical possibility. Scientists can build models, calculate structures, predict temperatures and brightness, and compare those predictions with observations, but the universe still has to provide evidence strong enough to separate a real dark star from more familiar objects that might look similar at great distance. That distinction is important. Science often becomes most interesting before the answer is secure. A good hypothesis does not need to arrive with a certificate of authenticity. It needs to be physically motivated, mathematically testable, and capable of making predictions that observations could support or reject. Dark stars meet that standard as a serious proposal, but they remain uncertain. There is no object we can point to tonight and say, without qualification, that one is definitely a dark star. There are distant sources that researchers have discussed as possible candidates, and new telescope data may help test the idea, but candidates are not confirmations. The early universe is crowded with objects that can imitate one another when seen from billions of light years away. A compact galaxy, an active black hole, a group of hot stars, and a single unusual star may all send us light that requires careful interpretation. You might compare it to seeing one glowing window on a distant hillside at night. It could belong to a house, a hotel, a workshop, or someone who has fallen asleep with every lamp switched on. The light is real. The source requires investigation. This is where powerful space telescopes enter the story. Instruments designed to detect infrared light can study objects so distant that the expansion of space has stretched much of their original light into longer wavelengths. Researchers can examine brightness, colour, apparent size, and spectral features, looking for patterns that fit models of dark stars better than competing explanations. Even then, the task is delicate. A dark star would not carry a sign reading, "Powered by invisible particles. Please observe responsibly." Scientists would need to infer its nature from the light it produces and from the environment around it. They would ask whether the object is too bright to be an ordinary star, too compact to be a normal galaxy, or whether its spectrum contains features expected from a very large, cool, primordial object. The word cool needs some care here. In astronomy, cool is a relative term. A surface temperature of several thousand degrees is still more than enough to discourage casual contact. Compared with the very hot surfaces expected for many ordinary first stars, however, a dark star could be considered cool. It might be large and swollen, giving it an enormous surface area from which to radiate energy. That combination could make it remarkably luminous without requiring the same surface temperature as a compact fusion-powered star. It is one of the pleasant oddities of stellar physics that a star can be cooler at the surface and still shine with tremendous total brightness if it is large enough. A small electric heater can be hotter than a warm wall, but a very large warm wall may release more total heat. Scale has a habit of making intuition file a formal complaint. Some models suggest that dark stars could begin with modest stellar masses and grow by drawing in surrounding gas. Because their surfaces might remain relatively cool, they could produce less of the intense ultraviolet radiation that normally pushes gas away from very hot first stars. With weaker feedback interrupting the flow, they might continue accreting for longer and become hundreds, thousands, or perhaps far more times the mass of the Sun, depending on how the dark matter fuel is supplied and how the surrounding environment behaves. That possibility is one reason dark stars attract attention beyond the subject of unusual stellar power. The early universe contains extremely massive black holes that seem to have grown surprisingly quickly. Astronomers continue to investigate how such black holes acquired so much mass so early. A very massive dark star could eventually collapse and leave behind a large black hole seed, giving later growth a substantial head start. It would not solve every problem automatically. The formation rates, lifetimes, fuel supply, and later evolution all matter. The object would need to form in the right location, remain supported long enough, collect enough gas, and then produce a remnant capable of continued growth. The early universe is not known for simplifying paperwork, but the connection is tempting. Start with a cloud of primordial gas inside a dark matter halo. Allow dark matter heating to delay normal contraction. Let the object grow while remaining broad and relatively cool. When the dark matter energy source weakens, the star changes. Fusion may become important. Collapse may follow later. A massive black hole may remain. In one sequence, an invisible particle process could influence the birth of a star and the eventual appearance of a black hole millions or billions of times more massive than the Sun. There is something else in the name that deserves attention. The phrase, dark star, has been used for more than one kind of object. In older discussions of gravity, it could refer to an object whose pull was so strong that light could not escape, an early relative of what we now call a black hole. The dark stars we are discussing tonight are different. They are not dark because gravity traps all their light. They receive the name because dark matter provides the proposed power source. This can lead to confusion, especially when a title asks, "What is a dark star really?" The honest answer begins with a small pause and the phrase, "Which kind?" Fortunately, tonight we mean the modern theoretical objects connected to dark matter and the first stars. They would be stars in structure, at least broadly speaking. They would be held together by gravity. They would maintain a balance between inward attraction and outward pressure. Energy would move from their interiors toward their surfaces. They could emit light and heat. Yet the mechanism supporting them would distinguish them from the stars we know best. Our sun shines because fusion in its core converts hydrogen into helium, releasing energy. That process has supported the sun for billions of years and will continue doing so for billions more. A dark star would begin with a different arrangement. Dark matter annihilation could supply enough heat to prevent the gas from contracting, to the point where fusion dominates. The object might therefore remain larger and less dense than an ordinary star of comparable mass. This does not make fusion irrelevant forever. If the dark matter fuel were exhausted, displaced, or no longer replenished, gravity would gain ground. The star could contract, its center would become hotter, nuclear reactions could begin or strengthen. The dark star phase could end, and a more familiar stage of stellar evolution could follow. The phrase dark matter fuel can also be misleading if we picture a tank running down in a straightforward way. The dark matter might first become concentrated as ordinary gas collapsed inside a halo. Later, additional particles might be captured if they passed through the star, scattered from ordinary matter, lost energy and became gravitationally bound. Different models explore different ways of maintaining the supply. Whether those processes work efficiently depends on properties of dark matter that experiments have not yet established. So the same object could act as a test of two great unknowns at once: the identity of dark matter and the nature of the first stars. That is scientifically exciting, but it also means every conclusion carries assumptions. Change the particle properties and the heating changes. Change the density of the halo and the available fuel changes. Change the rate at which gas falls inward and the star's growth changes. Models allow researchers to explore these possibilities, but nature decides which combination, if any, actually occurred. For a bedtime science journey, this is a useful place to settle our expectations. We're not about to uncover a secret object that textbooks have somehow overlooked. We are going to examine a carefully developed possibility at the boundary between particle physics, astronomy, and cosmology. Some parts are based on well-tested physics, such as gravity, stellar structure, and the expansion of the universe. Other parts rely on dark matter behaving in a particular way. The goal is not to pretend that uncertainty has vanished. It is to understand what the idea claims, why scientists considered it, and what evidence would make it more convincing. And while we do that, there is no need to keep every number or unfamiliar term in active memory. You will not be tested in the morning. No one will arrive with a clipboard and ask you to derive a dark matter annihilation rate before breakfast. We can let the details appear gradually, examine them, and allow them to settle. If you find this kind of slow scientific exploration soothing, you can give the video a like and subscribe to Science for Sleep. It helps this quiet corner reach other people who enjoy learning about the universe without being shouted at by it. You can also leave your answer to that earlier question. What did you imagine when you first heard the phrase dark star? There are no marks for accuracy. The universe has been producing misleading names for a very long time, and astronomers have contributed enthusiastically. For now, get comfortable. Let your breathing remain easy. There is nothing you need to solve tonight. We are simply following a question backward through cosmic history. To understand what happened inside those deepening pockets of gas and dark matter, it helps to begin at a time when the universe had no stars at all. There were no galaxies in the familiar sense, no planets, no glowing clouds shaped by nearby suns, and no points of light scattered across a black sky. The universe was not empty, and it was not inactive. but it had not yet built anything capable of shining for long periods. Matter was present everywhere. Gravity was already working. The first structures were beginning to develop. What was missing was a source of visible light. The period is commonly called the Cosmic Dark Ages. The name can sound as though something had gone wrong, as if the universe had suffered a large power cut and was waiting for someone to locate the fuse box. Nothing had failed. Darkness was simply the expected condition after the early radiation had faded from visible wavelengths and before the first stars began to produce new light. Reaching that period requires us to move back past every star and galaxy, past the first atomic nuclei, and toward the hot early universe. Soon after the Big Bang, space was filled with a dense mixture of radiation and particles. Temperatures were so high that electrons could not remain attached to atomic nuclei for long. Matter existed largely as an ionized plasma, with free electrons moving among positively charged nuclei. Photons repeatedly scattered from those charged particles, so light could not travel freely across great distances. A useful comparison is a thick fog. Light exists inside a fog, but it is scattered again and again, preventing a clear view through it. The early universe was not a weather system and did not contain water droplets, but it was similarly opaque. A photon trying to move in a straight line had very little chance of enjoying the journey. As the universe expanded, it cooled. Roughly 380,000 to 400,000 years after the Big Bang, conditions became cool enough for electrons to remain bound to nuclei, producing neutral atoms, mainly hydrogen and helium. Cosmologists call this stage recombination, although it was really the first lasting combination of these particles, rather than a reunion after a previous domestic disagreement. With far fewer free electrons available to scatter photons, radiation could begin travelling across space much more easily. That released radiation is observed today as the cosmic microwave background, stretched by cosmic expansion from much shorter wavelengths into the microwave part of the spectrum. The universe had become transparent, but transparent does not mean brightly illuminated. There were still no stars. An observer placed there with ordinary human eyes, suitable protection, and a very generous travel arrangement would not have seen the neat star field we associate with space. The background radiation was cooling and shifting toward wavelengths the eye could not detect. Ordinary matter had formed atoms, but those atoms were spread through space rather than gathered into luminous objects. This is the starting point of the long interval before the first stellar light. The exact boundaries depend on how the term is being used. Some researchers reserve dark ages for the period after recombination and before the first stars. Others use it more broadly for much of the era before cosmic reionization was complete. For our purpose, the important stretch begins when the universe became transparent and continues until the earlier stars started changing their surroundings. Although the scene would have appeared dark, it was not perfectly smooth. Tiny variations in density had been present from very early times. Some regions contained slightly more matter than average, while others contained slightly less. The differences were small, but gravity does not require a dramatic beginning. A slightly denser area exerts a slightly stronger pull. It attracts more material, becomes denser, and strengthens its pull further. Given enough time, a minor irregularity can grow into a major structure. You can picture a nearly level sheet with shallow dips across its surface. Roll small beads over it, and they will gradually collect in the dips. As more beads gather, the depressions deepen and attract still more. The early universe was three-dimensional, expanding, and governed by much more complicated physics than a sheet on a table, but the basic pattern is similar. Matter gathered where gravity had already gained a small advantage. Dark matter played a central role in this growth. Unlike ordinary matter, it did not interact strongly with the radiation filling the early universe. Ordinary gas had been tightly connected to light before recombination, and pressure resisted its collapse on small scales. Dark matter could begin building gravitational structure earlier. It collected into extended concentrations known as halos. After ordinary matter became neutral and less influenced by radiation, gas could fall more effectively into those dark matter wells. A dark matter halo is not a hard shell around an empty center. It is a region containing a higher concentration of dark matter, with density generally increasing toward the middle. The word halo is convenient, though it can suggest something neat and circular hovering over the head of a well-behaved galaxy. Real halos are broad gravitational structures. They grow, merge, stretch, and respond to the matter moving through them. During the Dark Ages, the smallest early halos provided the locations where the first gas clouds could begin serious collapse. These early systems are often called mini-halos. The mini is relative. Many had masses equivalent to hundreds of thousands or millions of suns. That is small compared with a galaxy-sized halo, but not small compared with anything one would want to find under the bed. Simulations of primordial star formation commonly place the first stars inside dark matter halos of roughly this scale, forming at very high redshift when the universe was only tens to a few hundreds of millions of years old. Gas falling into a mini-halo did not move gently to the center in a tidy queue. It accelerated under gravity, collided, compressed, and heated. Different streams could arrive from different directions. The halo itself could merge with smaller structures. Rotation might develop. Turbulence could appear. Even the first star-forming clouds had enough complications to make a simple diagram look slightly overconfident. Gravity alone can make gas denser, but collapse cannot continue efficiently unless the gas can get rid of heat. When particles fall inward, gravitational energy is converted into thermal motion. The gas heats up, pressure rises, and that pressure pushes back against further compression. Cooling allows energy to escape, reducing the pressure and helping gravity continue the collapse. Modern star-forming clouds have several ways to cool. They contain heavier elements such as carbon and oxygen. They contain dust grains. They can radiate energy through many atomic and molecular transitions. The first gas clouds had none of that equipment. The early universe produced mostly hydrogen and helium, with tiny traces of a few light elements. Carbon, oxygen, silicon, iron, and the other heavier elements had not yet been manufactured inside stars, because there had been no stars to manufacture them. Astronomers often call every element heavier than helium a metal, which is useful professionally and confusing almost everywhere else. Oxygen is therefore a metal in astronomical conversation, even though placing an oxygen cylinder beside a stack of iron bars may not make the classification feel more natural. The first star-forming gas was described as metal-free because it had not been enriched by earlier generations of stars. Without metals and dust, primordial gas had difficulty cooling to low temperatures. Atomic hydrogen can radiate efficiently once the gas becomes hot enough, but many early mini-halos were not massive enough to heat their gas to the temperatures where atomic cooling became effective. A different mechanism was needed. The answer came from a small amount of molecular hydrogen. A normal hydrogen atom contains one proton and one electron. Molecular hydrogen, written H2, contains two hydrogen atoms bound together. It was rare in the early gas, but even a trace amount could make an important difference. Collisions could excite the molecule into higher rotational or vibrational states. When it returned to a lower state, it emitted radiation, carrying energy away from the cloud. The process was not extremely efficient, but it was efficient enough to allow gas in suitable mini-halos to cool to a few hundred degrees above absolute zero and become denser. A few hundred degrees may sound warm for a cooling process. In ordinary life, it would be a poor setting for a bedroom and an excellent way to reconsider ownership of the furniture. In a collapsing primordial cloud, however, it was cool enough to reduce pressure substantially. The gas could settle toward the central region of the halo, where density continued to rise. The chemistry behind molecular hydrogen formation was delicate, because the universe did not begin with a convenient supply of H2. Reactions involving free electrons and temporary negative hydrogen ions helped build it. The details depend on density, temperature, and the remaining fraction of free electrons. A tiny chemical minority therefore controlled whether a much larger cloud could cool and collapse. The early universe had already discovered the principle that a small technical department can determine the schedule for everyone else. Not every halo became a stellar nursery. Some were too small to hold their gas effectively. Some could not produce enough molecular hydrogen. Gas could be disturbed by mergers or by motion between ordinary matter and dark matter left over from the early universe. Later, once the first stars appeared, ultraviolet radiation could break molecular hydrogen apart in nearby regions and delay additional star formation. The path from a dark halo to a shining star depended on local conditions, rather than a single universal timetable. Where cooling succeeded, the central gas became increasingly concentrated. At first, the dark matter dominated the mass and shaped the broad gravitational well. As gas moved inward, ordinary matter became much more important near the centre. Density increased over many orders of magnitude. The cloud developed a compact core surrounded by material that could continue falling inward. At this point, it is useful to separate two forms of darkness that are easy to mix together. The universe was dark because there were no luminous stars. The halos were dominated by dark matter because most of their mass did not emit light. These are related facts, but they are not the same fact. The cosmic dark ages were an era. Dark matter is a proposed form of matter. One describes a stage in cosmic history. The other describes a substance whose gravity helped create structure during that stage. Dark matter did not need to collide, cool, and settle into a thin central cloud in the same way as ordinary gas. Standard dark matter models treat its particles as weakly interacting, so they mostly move through one another and through ordinary matter. This produces a broad halo rather than a compact dark disk or dark gas cloud. Ordinary gas can radiate energy and sink toward the centre. Dark matter cannot easily shed energy, so most of it remains distributed over a much larger region. Even so, the dark matter density could be highest near the middle of the halo. As ordinary gas accumulated and deepened the central gravitational potential, the distribution of dark matter could respond, becoming more concentrated around the forming core. This response is important for the dark star idea. The proposed heating depends strongly on dark matter density. A small amount of dark matter, compressed into the right place, could influence how the gas behaved at the moment a protostar was trying to form. Before reaching that moment, the cloud had to continue cooling and contracting. Increasing density changed the chemistry. Molecular hydrogen became more abundant. Collisions occurred more frequently. At high enough densities, the gas became less transparent to its own cooling radiation. Energy that had once escaped freely began to get trapped. The collapsing core then entered a stage where its internal temperature, pressure, and chemical state changed rapidly. In the standard picture, the centre eventually becomes a protostellar object. It is not yet a stable, fusion-powered star. It is a dense core gaining mass from the surrounding cloud. Material falls toward it, often through a rotating disk. Accretion releases energy. The young object contracts, heats, and evolves toward the conditions needed for sustained nuclear fusion. The first stars are called Population 3 stars. The label may sound as if two earlier populations had already completed their paperwork, but the numbering arose from the historical classification of observed stars. Population 1 stars, including the Sun, are relatively rich in heavy elements. Population 2 stars are older and more metal-poor. The hypothetical first generation, containing essentially no metals, was named Population 3 afterward. Because primordial gas cooled less effectively than modern star-forming gas, early calculations often predicted very massive first stars. Later simulations showed a more complicated picture, including disks, fragmentation, multiple protostars, and a range of possible masses. The exact distribution remains an active area of research. It is still reasonable to expect that many first stars were more massive than typical stars forming in the present Milky Way, but the old picture of one identical enormous star in every mini-halo has become less certain. Whatever their final masses, the first conventional stars changed the universe dramatically. They produced visible and ultraviolet light. Their radiation heated and ionized surrounding gas. Their cores began manufacturing heavier elements. Some exploded, spreading those elements into nearby space. Others may have collapsed into black holes. Each new source altered the conditions for the objects that formed later. The end of the Dark Ages was therefore not like a lamp switching on everywhere at once. The universe is far too large and disorganized for such punctual behavior. The first stars appeared in isolated regions. Around each source, light spread through the surrounding gas. More stars formed elsewhere. Small galaxies assembled. Luminous regions grew and overlapped over time. Cosmic dawn was patchy, gradual, and different from place to place. The ultraviolet light from early stars and accreting black holes eventually contributed to ionization, when much of the neutral hydrogen between galaxies became ionized again. Recombination had allowed electrons to join nuclei and made the universe transparent. Ionization later separated many of those electrons again, but the universe did not return to its earlier opaque state because the matter had expanded and become much more diffuse. The same basic ingredients can behave very differently when the density changes. Dark stars, if they existed, would belong near the beginning of this transition. They would form out of the same primordial hydrogen and helium expected to create population 3 stars. They would sit inside the same dark matter mini-halos. Their gas would follow much of the same early collapse. The difference would emerge when the central density became high and dark matter heating began to compete with the cooling of the gas. The original dark star proposal identified a possible point at which energy from annihilating dark matter particles could become strong enough to slow or halt the ordinary collapse toward a fusion-powered star. Under the assumptions used in those models, the result would be a large hydrogen and helium object supported by dark matter heating. Other studies have explored how sensitive that outcome is to the dark matter profile, particle properties, and structure of the collapsing cloud, which means the idea remains dependent on physics that has not been confirmed. This possibility gives the phrase "before the first sunrise" a more precise meaning. The earlier stellar objects may not all have followed the standard route from collapsing gas to fusion. Some might have paused in a different state, drawing energy from dark matter before their centers became ordinary stellar furnaces. If that happened, cosmic dawn may have included stars that were cooler at the surface, larger in radius, and powered by a process that modern astronomy has never directly observed. There is an important caution here. The cosmic dark ages are part of the standard history of the universe, supported by observations of the cosmic microwave background, large-scale structure, distant galaxies, and the intergalactic medium. Dark stars are not established in the same way. They are a proposed consequence of particular dark matter models operating under particular conditions. We can describe the environment in which they might form with considerable confidence, but the last step remains hypothetical. That is why the environment matters so much. A dark star cannot simply appear anywhere. It requires primordial gas, a dense dark matter halo, continuing collapse, sufficient heating, and a way for the released energy to remain in the gas rather than escape. Remove any one of those conditions and the object may proceed along a more familiar path. The long darkness before the first stars supplied the right laboratory. There were no heavy elements to dominate cooling. Dense mini-halos gathered both dark matter and gas. The first protostellar cores formed near the centers of those halos, exactly where the dark matter concentration could be greatest. The universe had arranged the ingredients in the same place, although whether they actually produced a dark star depends on what dark matter particles are and how they behave. Consider one of those mini-halos in more detail. It may contain the mass of 1,000,000 suns spread over a large region, most of it in dark matter. Primordial gas drifts inward and heats. A trace of molecular hydrogen lets it cool. The gas becomes denser and falls farther toward the center. Its own gravity begins to matter. the central core shrinks. Around it, more material remains available for accretion. At the same time, the changing gravitational field draws dark matter orbits inward. The dark matter does not form a solid center, but its density around the gas core may rise. If the particles can annihilate with themselves, the rate of energy production increases rapidly as the density grows. At low density, the effect is negligible. At high density, it might no longer be. The next question is therefore not whether the early universe was dark. We know why it lacked stars and how gravity began assembling the first star-forming clouds. The question is what happened inside one cloud when cooling gas, rising pressure, increasing dark matter density, and the first stages of stellar collapse all met in the same central region. That change in the energy balance would begin quietly. There would be no explosion, no sudden flash, and no clear moment when a dark star announced that it had arrived. A cloud of primordial gas would already be collapsing inside a dark matter halo. Hydrogen molecules would be carrying heat away. Gravity would be pulling the gas inward. Density would be rising. The central region would be getting smaller and hotter. Then, as the dark matter became more concentrated and its annihilation products became harder to escape, an additional source of heat could begin to matter. The object would not be a star at first. It would be a collapsing protostellar core surrounded by a much larger supply of gas. Most of its mass would be ordinary matter, mainly hydrogen and helium. Dark matter would contribute only a tiny fraction of the material near the center. Its importance would come from the amount of energy that could be released when its particles interacted. The original dark star calculations focused on a class of hypothetical particles known as weakly interacting massive particles, usually shortened to WIMPs. These particles were considered attractive dark matter candidates because they could have been produced in the early universe in roughly the abundance needed to explain the dark matter observed today. In many versions of the idea, a WIMP is its own antiparticle. When two WIMPs meet, they can annihilate, converting their mass into other particles and energy. Dark stars do not require every possible kind of dark matter to behave this way. They require a form of dark matter that can annihilate and release energy under the conditions found inside a forming primordial star. The word annihilation can make the process sound as though matter simply disappears. What it really means is that the original particles are transformed. Their mass becomes energy and other particles, in keeping with the same mass-energy relationship that appears throughout modern physics. Some of the products might be photons, some might be electrons or related particles. Neutrinos could also be produced depending on the annihilation process. The exact mixture would depend on the identity of dark matter, which remains unknown. At low gas densities, much of this energy would escape. A few annihilations inside a thin cloud would not automatically create a star. The resulting particles could travel outward without transferring enough energy to change the collapse. The gas would continue cooling, and gravity would continue pulling it inward. Dark matter heating would be present in the equations but unimportant in the outcome, rather like one person attempting to warm a warehouse by holding a cup of tea. As the gas became denser, that situation could change. Electrons and photons produced by annihilation would have more chances to collide with ordinary matter. Instead of leaving the core, they could deposit part of their energy inside it. Neutrinos would still escape easily because they interact so weakly, but other products could become trapped well enough to heat the gas. The early proposal identified this trapping as one of three necessary conditions for a dark star. The dark matter density must be high. The annihilation products must deposit a substantial fraction of their energy, and the resulting heating must become stronger than the cooling processes trying to remove that energy. Those three requirements are straightforward to list, but reaching them would involve a long sequence of changes. The first requirement begins with the dark matter halo itself. Before ordinary gas formed a dense core, dark matter would already be concentrated toward the central region of the halo. It would not form a solid ball. Its particles would move on many different orbits, passing through the inner and outer parts of the halo. Even so, the average density would rise toward the center. When gas cooled and fell inward, it deepened the gravitational potential. The dark matter orbits could respond to that change. Some of the dark matter would shift towards smaller radii, raising the density around the contracting gas. This process is often called adiabatic contraction. Here, adiabatic does not mean that the system is placed inside an insulated container. It means that the gravitational potential changes slowly enough for certain properties of the particle orbits to adjust in a predictable way. A simple way to picture this is to imagine runners moving around a broad circular track while the track is gradually tightened. The runners would be forced into a smaller region, even though they had not suddenly changed what they were made of. Dark matter particles would not be following neat lanes, and their orbits could be elongated rather than circular, but the general effect is similar. The inward movement of ordinary gas changes the gravitational environment, and the dark matter distribution becomes more concentrated. Researchers have tested this idea with more detailed calculations that allow dark matter particles to follow non-circular orbits. Those studies found that baryonic infall could raise the central dark matter density enough for annihilation heating to become significant under the assumed WIMP model. The result depends on the halo structure and on how the gas collapses, but the concentration is produced by gravity rather than by dark matter cooling like ordinary gas. The second requirement develops as the ordinary gas becomes opaque to the annihilation products. Early in the collapse, the core is too thin to hold much of the released energy. Later, particles produced in annihilations encounter more material before reaching the edge. Each interaction passes some energy to the gas. Once enough energy remains inside, dark matter annihilation becomes an actual heating mechanism rather than a minor source of escaping radiation. The third requirement is a competition. Primordial gas cools mainly through molecular hydrogen during this stage. Collisions excite the molecules, and the molecules release photons as they return to lower energy states. Those photons carry heat away if they can escape. At increasing density, however, molecular cooling becomes less effective. The gas can become optically thick to some of its own radiation. Collisions can also alter or destroy hydrogen molecules. Meanwhile, the annihilation rate rises sharply as the dark matter density increases. That sharp increase comes from a simple statistical reason. Annihilation requires two dark matter particles to meet. If the number of particles in a given volume doubles, the number of possible pairs rises more than twofold. The heating rate is therefore proportional to the square of the dark matter density, divided by the particle mass and multiplied by the annihilation cross-section. In ordinary language, concentrating the particles makes encounters much more common. A crowded railway platform produces more accidental shoulder bumps than the same number of people spread across an empty field. The collapse therefore creates conditions that favour dark matter heating in two ways. It raises the dark matter density, increasing the number of annihilations, and it raises the gas density, helping the released energy remain trapped. Cooling is still operating, but it no longer has the entire budget to itself. In the original benchmark calculations, the point at which heating overtook molecular hydrogen cooling depended strongly on the assumed WIMP mass. For a commonly used example involving 100 gigaelectron-volt WIMPs, the transition occurred when the hydrogen number density reached roughly 10 trillion particles per cubic centimetre. Different particle masses shifted the threshold. These figures are model-dependent rather than universal birth measurements, but they show how far the collapse must proceed before dark matter heating becomes decisive. 10 trillion hydrogen particles in a cubic centimetre sounds extremely dense compared with ordinary interstellar gas, but it is still diffuse compared with familiar solid matter. A cubic centimetre of air near sea level contains vastly more particles. The early core could therefore be dense by astronomical standards while remaining far from the density of a table, a stone, or the device playing this video. Astronomy is generous with the word dense. Once the heating rate matched and then exceeded the cooling rate, the collapse would not stop as though it had struck a wall. The change would be gradual. Gas already moving inward would continue moving. The central structure would adjust. Temperature and pressure would rise. What matters is that the core could no longer lose energy quickly enough to maintain the previous rate of contraction. Pressure is the ordinary matter response to compression and heating. Gas particles move more rapidly as the temperature rises. Their collisions create an outward pressure gradient. Gravity still pulls inward, but the pressure begins offering stronger resistance. If the two effects reach balance, the object can enter hydrostatic equilibrium. Hydrostatic equilibrium is the basic arrangement that supports normal stars as well. At every depth, the weight of the material above is balanced by a change in pressure below. The center must support everything outside it, so the pressure is highest there. Moving toward the surface, less material remains overhead, and the pressure falls. A star is not held up by a hard shell. It is supported throughout its interior by this continuous balance. In a conventional star like the Sun, fusion supplies the energy needed to maintain that structure over long periods. In the proposed dark star, annihilation heating would supply the early support. The object would still radiate energy from its surface. If it radiated more energy than annihilation replaced, it would contract and heat until the energy production rose or another source became important. If heating exceeded the energy lost from the surface, it would expand and cool. Stable configurations would occur where the production and loss rates matched closely enough. This is why a dark star should not be pictured as gas that has simply stopped collapsing. It would be a self-regulating object. A slight contraction could raise the dark matter density and increase annihilation heating. Extra heat could expand the gas, reducing the density and lowering the annihilation rate. The details are complicated because the dark matter distribution responds to the ordinary matter, but the broad feedback can create an equilibrium rather than a permanent stall. The first stable object in early models was modest in mass compared with the giants it might later become. Calculations placed the initial hydrostatic core at around a solar mass, with a radius measured in astronomical units, rather than in the much smaller dimensions of an ordinary protostar. One frequently quoted benchmark found a core of about 6/10 of the Sun's mass, and roughly 17 astronomical units across at the point when dark matter heating took control for a 100 giga-electron-volt WIMP. An astronomical unit is the average distance between Earth and the Sun, so this early object would already be spread across a region comparable with part of our solar system. Those numbers depend on the assumptions, but the main prediction is consistent. The first dark star would be large and diffuse. Calling it diffuse does not mean it would be fragile in the everyday sense. Its total mass would still create substantial gravity. The point is that its material would be distributed through a much larger volume than the matter in a normal star of similar mass. Its average density could be low, and its surface gravity could be weaker than one might expect from the word star. The gas surrounding the new object would not disappear when equilibrium began. The dark star would sit inside a larger collapsing cloud, with material continuing to move toward the center. Angular momentum would likely produce a disk or flattened inflow. Gas from that environment could accrete onto the star, adding mass. Each addition would force the internal structure to readjust. Accretion is not a polite process. Gas falling toward a star gains speed. It can strike the surface or pass through a disk, converting gravitational energy into heat. Shocks may form, radiation must work its way outward. Even without dark matter, accreting protostars are complicated. A dark star adds another energy source whose strength depends on a component that is not moving and cooling in the same way as the gas. As ordinary matter accumulated, the dark star could contract slightly under its increasing weight. That contraction would draw the dark matter distribution inward again. More dark matter in the stellar region would mean more annihilation heating. The added heat would help the star settle into a new equilibrium at the larger mass. Models therefore build dark stars step by step. Add a small amount of gas, calculate the new structure, adjust the dark matter profile, estimate the annihilation luminosity, and repeat. This growth creates an unusual relationship between the fuel and the star. In a normal fusion-powered star, the fuel is part of the star's main mass. Hydrogen in the core is gradually converted into helium. In an early dark star, almost all the mass is still hydrogen and helium, but that material is not initially providing most of the power. Dark matter may account for less than 1/1000th of the total mass, while supplying enough energy to support the entire object. The reason is efficiency. Fusion releases only a fraction of the rest mass energy of the hydrogen that participates in the reaction. Annihilation can convert a much larger fraction of the dark matter particle mass into energy. Some energy leaves as neutrinos and is lost to the star, but the fraction deposited in the gas can still be substantial. A very small amount of dark matter can therefore have an effect far out of proportion to its mass. This does not provide unlimited power. The central reservoir created by adiabatic contraction can be depleted. Annihilating particles are removed from the supply. Orbits that pass through the star may eventually be emptied faster than they are replenished. The surrounding halo contains much more dark matter, but not all of it travels through the dense stellar region. Gravity alone does not guarantee that fresh particles will arrive at the rate needed forever. A second fueling mechanism may become possible later. Dark matter particles passing through the star could scatter from atomic nuclei, lose kinetic energy, and become gravitationally bound. After repeated passages and further scattering, they could settle nearer the center, where annihilation would resume. This process is called capture. It depends on dark matter interacting with ordinary matter, not merely through gravity but through a weak scattering process, since the relevant cross-sections are constrained but not known to be non-zero. Capture introduces another major uncertainty. Early dark star formation is usually described first with the dark matter brought inward through gravitational contraction, while capture is considered as a possible way to extend or revive the dark-powered phase. The distinction matters because the star's birth should not be imagined as a single switch that remains permanently on. The initial dark matter supply, the accretion of gas, the response of the halo, and possible later capture all operate on different timescales. A dark star could grow while one reservoir lasts, contract when the supply weakens, and alter its structure again if another source of dark matter heating becomes effective. There are also reasons the birth might fail. The central dark matter density may be lower than required. The gas may not remain aligned with the densest part of the halo. Fragmentation could produce several protostars that disturb the central distribution. Mergers, rotation, and gravitational interactions could move the forming star away from the dark matter cusp. The annihilation products might deposit too little energy. Dark matter might not be made of annihilating particles at all. Different calculations have also produced different estimates for how long the initial dark-powered state could last. Some stellar evolution studies describe the phase created by gravitational contraction as temporary, after which the object resumes contraction toward fusion. Other dark star models find equilibrium configurations that can continue growing through accretion, while dark matter remains available. The difference reflects assumptions about the dark matter distribution, gas inflow, stellar structure, and how efficiently the fuel is replenished. That uncertainty should remain visible in the narration because Might Be Born is doing important work. The idea is physically motivated, and detailed stellar models can describe what the object would look like after equilibrium is established. The uncertain step is whether real primordial clouds followed the required route often enough to create a population of dark stars. Suppose one cloud did. Near the center of a mini-halo, a collapsing gas core reaches the point where annihilation heating can no longer be ignored. The temperature rises above the track expected from molecular cooling alone. Pressure slows the contraction. Energy released by a tiny dark matter component is deposited through the ordinary gas. The object expands into a broad hydrostatic configuration. Gas outside continues falling inward. The dark star has not ignited in the conventional sense because sustained hydrogen fusion is not yet its main source of power. Nothing about the view from outside would reveal the birth mechanism immediately. The object would radiate because energy was moving through its gas and escaping from the surface. It might appear bright rather than dark. Its colour and spectrum would depend on its surface temperature and atmosphere. The evidence for dark matter heating would come from the combination of its size, luminosity, temperature, growth, and evolutionary behaviour, not from a visible patch of darkness at the centre. The name becomes clearer once the bookkeeping is understood. It is a star built mainly from ordinary matter, held together by ordinary gravity, and shining through ordinary radiation. It is called dark because an unseen component supplies the heat that allows the stellar structure to exist before fusion takes over. The arrangement inside the star would be unusual, but it would still obey the same basic rules that govern every other self-gravitating ball of gas. Gravity would pull all of the material toward the centre. Pressure would resist that pull. Energy would be produced in the interior, carried outward through the gas, and released from the surface as radiation. The difference would lie in where that energy came from and how widely it was distributed. In the Sun, most of the power is generated in a compact central region, where the temperature and density are high enough for hydrogen nuclei to fuse. The rate of fusion is extremely sensitive to temperature. A slightly hotter core can produce much more energy, so the Sun regulates itself through expansion and contraction. If the core heats too much, the gas expands, the density and temperature fall, and fusion slows. If it cools, gravity compresses it, the temperature rises, and fusion strengthens. A dark star would also regulate itself, although the central heater would not be an ordinary fusion core. Dark matter particles passing through the interior could annihilate wherever their density was high enough. The heating rate would be greatest near the centre, because that is where the dark matter concentration would usually be highest. But the energy source could extend through a larger fraction of the object than fusion does in an ordinary star. That distribution changes the structure. Fusion-powered stars need very hot, dense centres, because atomic nuclei must overcome their electrical repulsion before they can join. Dark matter annihilation, in the proposed models, does not wait for hydrogen to reach fusion temperatures. It depends mainly on the density and particle properties of the dark matter. If enough annihilation energy is deposited in the gas, the star can remain supported while its ordinary matter is comparatively cool and spread out. The dark matter itself would not form a glowing central lump. It would be mixed through the same volume in the sense that its particles would pass through the ordinary gas, but the two components would behave differently. Hydrogen and helium atoms would collide frequently, exchange energy, produce pressure, and respond as a fluid. Dark matter particles would move through the star on gravitational orbits and interact only rarely with ordinary matter. They would be present without behaving like part of the gas. Imagine a crowded railway station filled with people, while a much smaller number of fast-moving insects fly through the building without paying attention to corridors, doors, or platform signs. The people collide, form queues, and create pressure in narrow spaces. The insects cross the same region, on completely different paths. It is not a perfect comparison, especially for the insects, but it captures the fact that ordinary matter and dark matter could occupy the same star without sharing the same kind of motion. When two suitable dark matter particles met and annihilated, their mass would be converted into energetic products. Some of those products would interact with the hydrogen and helium around them. Electrons, positrons, and photons could transfer energy through collisions and scattering. Neutrinos would escape much more easily, carrying away a fraction of the energy. The exact division would depend on the unknown dark matter particle and its annihilation channels. Early dark star models often assumed that roughly 2/3 of the annihilation energy could remain in the star once the gas became dense enough, with the rest leaving mainly through neutrinos. That fraction was not a universal law. It was a useful benchmark based on the expectation that most non-neutrino products would eventually deposit their energy in the thick stellar material. Change the particle model, and the fraction can change with it. Once deposited, the energy would quickly lose any visible connection to its exotic origin. an energetic electron created in an annihilation would strike ordinary particles. Those particles would strike others. The energy would be shared through the gas and converted into thermal motion. By the time it reached the surface, it would not emerge carrying a small label that said dark matter. It would appear as ordinary electromagnetic radiation. This is an important point because a dark star would shine with normal light. The power source would be invisible, but the output would not be. A toaster powered by electricity does not produce electrical-looking toast. In the same way, a star powered by dark matter annihilation would still release heat and photons through ordinary matter. The star's total luminosity would be set by the rate at which energy was produced and escaped. In equilibrium, the power generated by dark matter annihilation, along with any smaller contributions from contraction, accretion, or fusion, would closely match the energy radiated from the surface. If the star produced more than it lost, its internal energy would rise and the gas would expand. If it lost more than it produced, it would contract and become denser. Expansion would reduce the ordinary gas density, but it could also alter the dark matter distribution and lower the annihilation rate. Contraction would have the opposite effect. This creates a thermostat. It is not controlled by a dial, and it would be unwise to search for one, but the response of gravity, pressure, and heating could keep the star near a stable configuration. The thermostat would work because annihilation heating depends strongly on dark matter density. Pack the dark matter particles into a smaller region, and they encounter one another more often. Spread them out, and the encounter rate falls. Since 2 particles are needed for each annihilation, the energy production rises approximately with the square of the density. A modest structural change can therefore produce a larger change in the heating rate. That does not mean the star would pulse wildly whenever a few particles moved. Stellar material responds over characteristic timescales. Pressure disturbances travel through the gas. Radiation and convection transport energy. Gravity adjusts the overall structure. Stable models are those in which these effects settle into a balance rather than amplifying into disruption. To calculate that balance, researchers use the same stellar structure equations applied to conventional stars. One equation describes how the mass enclosed within a given radius increases as we move outward. Another describes hydrostatic equilibrium, matching the pressure gradient against gravity. A third tracks how luminosity changes with radius as energy is produced. A fourth describes the temperature gradient required to carry that energy outward. These equations do not care whether the energy came from fusion, gravitational contraction, or dark matter annihilation. The source enters through the energy generation term. Replace the usual nuclear reaction rate with an annihilation heating rate. Supply a model for the dark matter density, and the equations can be solved for the star's radius, temperature, pressure, density, and luminosity. The first calculations often treated dark stars as polytropes. A polytropic model relates pressure and density through a simple mathematical rule. It does not capture every detail of a real stellar interior, but it is useful for finding stable structures and understanding how they change as mass is added. Later work used more detailed stellar evolution software and found the same broad result. Dark matter heating can produce very large, relatively cool stars while the fuel remains available. Inside a low-mass dark star, energy transport could be dominated by convection through much of the interior. Convection occurs when hotter, less dense material rises, while cooler, denser material sinks. It is the same general process seen in boiling water, although stellar convection involves compressible plasma, radiation, enormous pressure, and no helpful glass lid. A rising parcel of gas carries energy with it. As it moves into regions of lower pressure, it expands and cools. Cooler material can move downward and be reheated. This circulation transports energy more efficiently than radiation alone when the temperature gradient becomes steep enough. In stellar calculations, the decision between radiative and convective transport depends on whether a small displaced parcel continues rising or returns to its original position. As the dark star gained mass, its internal structure could become more radiative. Radiative transport does not mean photons travel directly from the center to the surface without interruption. Inside an opaque star, a photon may be absorbed and re-emitted or scattered an enormous number of times. Energy moves outward through a slow, random process. The individual photons eventually leaving the surface are not necessarily the same photons created deep inside. This journey can be compared with trying to cross a packed room while changing direction after every step. The exit may be visible in principle, but reaching it becomes a long and statistically irritating experience. In a star, the difficulty depends on opacity, which measures how strongly the material blocks the flow of radiation. Primordial hydrogen and helium provide opacity through several processes. Electrons can scatter photons. Atoms and ions can absorb radiation. The exact opacity changes with temperature, density, and ionization state. Since a dark star is cooler than a conventional massive population 3 star at its surface, its outer layers can contain more neutral hydrogen and, under some conditions, molecular hydrogen. That affects both the atmospheric structure and the light that eventually escapes. The surface is not a solid boundary. There is no crust where the gas ends sharply and empty space begins. Density and pressure decrease gradually through the atmosphere. Astronomers usually define the visible surface near the depth from which photons can escape without being repeatedly scattered. The temperature associated with the total outgoing radiation is called the effective temperature. A dark star could have an effective temperature of several thousand to around 10,000 Kelvin during much of its growth in early models. That is extremely hot by ordinary standards, but cool for a very massive primordial star. A normal metal-free star with hundreds of solar masses could have a surface temperature several times higher, producing intense ultraviolet radiation. The dark star would be much larger, allowing it to release a huge luminosity from a cooler surface. The relation is simple in outline. A star's luminosity depends on its surface area and the fourth power of its effective temperature. A cooler surface emits less energy per square meter, but an enormous radius provides many more square meters. A dark star can therefore be cooler and still be millions of times as luminous as the Sun. Suppose a star were expanded until its radius reached several astronomical units. Its outer edge could extend beyond the orbit of Earth and perhaps toward the region occupied by the giant planets in our solar system, depending on the model and mass. The material would remain gaseous and gravitationally bound. It would not swallow planets because no planets would be forming safely inside it, which is one less concern for the imaginary estate agent. This swollen structure would keep the center cooler than it would be in a compact star of the same mass. Central temperature rises when gravity compresses matter into a smaller volume. By preventing deep contraction, dark matter heating delays the conditions required for strong hydrogen fusion. The ordinary fuel is present, but the star does not yet need to use much of it. Small amounts of nuclear burning could still occur. Deuterium, a heavy form of hydrogen, ignites at a lower temperature than ordinary hydrogen fusion. As the star grew and its center warmed, deuterium burning could contribute some energy. Later, hydrogen burning might begin. In a strongly dark matter-powered phase, however, these reactions would remain secondary because any extra heating would encourage the star to expand, reducing the central temperature and nuclear reaction rate. This is another form of regulation. Nuclear fusion tries to become important as the star contracts. Dark matter heating keeps the star expanded. If fusion adds noticeable power, expansion can cool the core and suppress it again. The star can remain outside the normal main sequence as long as the annihilation source is strong enough. The balance also explains why the object can continue accepting gas. Massive conventional first stars become very hot and produce strong ultraviolet radiation. That radiation ionizes nearby gas and heats it. Radiation pressure and expanding ionized regions can interfere with accretion, limiting further growth. A cooler dark star would release a smaller fraction of its luminosity as ionizing ultraviolet light. It could be extraordinarily bright while being less effective at pushing away its food. This does not remove all feedback. Radiation still exerts pressure. Accreting gas still releases energy. Rotation and disk structure still matter, but the cooler spectrum weakens one of the main processes expected to halt the growth of massive primordial stars. Gas may continue reaching the dark star for longer, allowing the object to become much more massive before feedback wins. The furnace is therefore unusual in two separate ways. Its fuel is almost absent from the star's mass budget, and its heat keeps the star cool enough to keep growing. That sounds contradictory only because temperature and total power are easy to confuse. The interior is hot, the surface is cooler than that of a comparable ordinary star, and the total luminosity is enormous because the emitting area is so large. Dark matter heating would not necessarily occur at one fixed rate throughout the entire life of the object. As gas accreted, the star's mass and radius changed. The dark matter distribution responded. The original reservoir was gradually consumed. Some particles on elongated orbits could continue passing through the star, while others might never approach the center closely enough to contribute. The amount of fuel needed is surprisingly small. Model calculations have found that dark matter could make up less than 1 part in 1,000 of the total stellar mass, while powering the star. A star with hundreds of solar masses might contain only a fraction of a solar mass in dark matter at any one time. Annihilation is efficient because much of the particle mass is converted directly into energy. Efficiency does not mean permanence. Each annihilation removes 2 particles from the reservoir. If no new particles replace them, the central supply declines. The star then radiates more energy than dark matter annihilation can provide. Gravity causes it to contract, and the contraction releases gravitational energy. The center heats. Fusion begins to take a larger role. Fresh dark matter could arrive in 2 broad ways. The first is continued gravitational rearrangement of the surrounding halo as ordinary gas accumulates. New orbits may be brought into the stellar region. The second is capture through scattering. A dark matter particle passing through the star might collide with an atomic nucleus and lose enough speed to become trapped by gravity. After more passages and collisions, it could settle into the center and eventually annihilate. Capture would turn the ordinary star into a net. The net would be almost completely transparent, and most particles would pass through untouched. But if the surrounding dark matter density were high, and the scattering probability were large enough, even rare collisions could build a useful supply over time. This possibility depends on particle properties that experiments have not measured. Dark matter must scatter from ordinary matter strongly enough to be captured, but weakly enough to remain consistent with direct detection limits. It must also exist at sufficient density around the star. Models can explore the allowed combinations, but no current observation establishes that early dark stars were refueled this way. There is also a geometrical problem. A forming star may not remain perfectly centered in the dark matter cusp. Gravitational interactions, fragmentation, or mergers can move it away from the region with the greatest density. A displacement that looks small compared with the halo can sharply reduce the available fuel. The furnace works best when the stove remains in the kitchen, which the early universe was under no obligation to arrange. Even if the star stayed centered, the dark matter halo itself would evolve. Other halos could merge with it. Gas inflow could become uneven. The central density profile could be disturbed. The star's radiation could alter the surrounding ordinary matter. Every process changes the conditions used in a simple equilibrium model. For that reason, a dark star should not be treated as one exact object with a single temperature, radius, and lifetime. It is a family of theoretical stellar configurations. The outcome depends on the dark matter particle mass, annihilation rate, scattering rate, halo profile, accretion rate, and the movement of gas and stars near the center. Different assumptions produce different sizes and growth histories. The broad features remain recognizable across many models. The star is made almost entirely of hydrogen and helium. A small dark matter component supplies much of the power. Hydrostatic equilibrium prevents collapse. Thermal equilibrium matches energy production with radiation. The radius is much larger than that of an ordinary massive star. The effective temperature is lower. Accretion can continue for longer because ultraviolet feedback is weaker. From outside, none of the internal particle interactions would be seen directly. An observer would measure the light leaving the photosphere. Its brightness and spectrum would reveal the effective temperature, chemical composition, surface gravity, and perhaps the presence of surrounding gas. Scientists would then compare those observations with models of stars, galaxies, and accreting black holes. That is one reason identification is difficult. An invisible furnace does not produce invisible smoke. It produces an object whose visible properties must be interpreted. A large young galaxy can be bright. A cluster of ordinary stars can be bright. Gas falling into a black hole can be bright. A single dark star could also be bright. Distance removes fine detail and leaves researchers with a limited set of clues. The most useful clues would come from combinations that are difficult for ordinary objects to reproduce. An extremely high luminosity paired with a relatively low effective temperature could suggest a very large emitting surface. A spectrum dominated by primordial hydrogen and helium would fit formation before significant chemical enrichment. The absence or weakness of signatures expected from an active galactic nucleus could count against a black hole explanation. None of these clues would be decisive alone. Before we reach the problem of observation, however, the structure itself needs closer attention. The invisible furnace explains where the energy comes from, but it does not yet make the star's scale intuitive. A body containing hundreds or thousands of times the Sun's mass might be expected to compress into an intensely hot, compact object. Dark matter heating produces nearly the opposite result. The star becomes broad, low in average density, and cool at the surface, even while its total output rises. The reason it can remain spread out is that size alone does not determine whether an object stays together. What matters is the balance between gravity and pressure throughout its interior. A dark star may have a radius extending across several astronomical units, but it also contains an enormous amount of mass. Every part of that mass attracts every other part. The outer gas is not drifting loosely through space. It is held inside a deep gravitational field, even though the star is much less compact than an ordinary massive star. The word puffy can therefore be slightly misleading. It makes the object sound soft, light, and vulnerable to a moderate breeze. There would be no breeze large enough to inconvenience it. A dark star containing hundreds of times the mass of the Sun would remain a powerful gravitational object. Gas near its surface might be relatively thin, but escaping completely would still require tremendous speed. Average density helps explain its unusual structure. Take a very large dark star and spread several hundred, or perhaps 1,000 solar masses through a sphere with a radius comparable to the size of the outer solar system. The average density could be far lower than the density of air near Earth's surface. That sounds almost impossible until we remember how much empty space can fit inside a sphere several astronomical units wide. Average density, however, does not tell us what every part of the star is like. The outer atmosphere would be extremely thin compared with the central region. Density would rise steadily as we moved inward. Pressure and temperature would rise as well because deeper layers must support the weight of everything above them. The center could be hot and compressed, even though the star as a whole remained broad and low in average density. A normal star has the same general pattern. The Sun's surface is far less dense than its core. The difference is that a dark star would be expanded far beyond the dimensions expected for a conventional star with the same mass. Its material would be arranged through a much larger volume, reducing the central compression and delaying the rise to the temperatures normally associated with strong hydrogen fusion. Dark matter heating is what maintains that expansion. Energy deposited in the interior increases the motion of ordinary particles. Faster moving particles create greater pressure. That pressure pushes outward against gravity. The star settles at the radius where its internal pressure profile can support its mass, while the energy leaving the surface is replaced by energy produced inside. If the star contracted slightly, the ordinary gas would become denser. The dark matter distribution near the centre could also become more concentrated, increasing the annihilation rate. More energy would then be deposited in the gas, raising the pressure and encouraging the star to expand again. If the star expanded too far, the density and annihilation rate could fall, reducing the heating and allowing gravity to pull the material inward. The response would not be instantaneous, but it provides a stabilizing tendency. The star could adjust its size until the inward and outward effects were closely balanced. Conventional stars perform a related adjustment through nuclear fusion. Dark stars use a different heat source, but gravity still acts as the manager who insists that the accounts must eventually agree. This behavior is connected to a strange property of self-gravitating systems. When an ordinary object loses heat, it usually becomes cooler. A star can do the opposite. If it loses more energy than it produces, gravity causes it to contract. Contraction converts gravitational energy into thermal energy, making the center hotter. A star can therefore lose energy and heat up at the same time, which is the sort of arrangement that would make a household thermostat consider a change of profession. As long as dark matter annihilation replaces the energy radiated from the surface, deep contraction is unnecessary. The central temperature remains below the level expected in a compact star of equal mass. Fusion may occur at a low rate, particularly as the star grows, but it does not have to provide most of the luminosity. The object remains outside the normal main sequence, supported by the invisible fuel passing through its interior. Most of the heating would occur toward the center, where the dark matter density was highest. The exact distribution would depend on how dark matter particles move through the star. Some would follow orbits that carried them repeatedly through the inner region. Others would spend most of their time farther out. Since the annihilation rate rises with the square of the density, even a moderate central concentration would make the inner parts responsible for a large fraction of the power. The deposited energy would then need to travel outward. It could not simply jump from the center to the surface. The ordinary gas would be opaque across much of the star, so energy would pass through it by convection, radiation, or a mixture of the two. Convection moves energy through the physical motion of material. A parcel of gas heated below can become less dense than its surroundings and rise. As it reaches lower pressure regions, it expands and cools. Other material sinks to replace it. Repeated across the star, this motion carries heat outward. The comparison with water heating in a saucepan is useful up to a point. Warm water rises, cooler water sinks, and circulating motion spreads the heat. Inside a star, there is no rigid pan, no clearly visible bubbling surface, and no one nearby asking whether it has boiled yet. The material is an ionized gas under enormous pressure, and the scale of the circulation can be larger than planets. Young or lower mass dark star models can be largely convective. Their interiors carry much of the annihilation energy outward through moving gas. Convection also mixes the ordinary material. Hydrogen and helium do not remain separated into neat shells. The star behaves more like a well-stirred body during this stage. As the object gains mass and its internal conditions change, radiation can become more important. Radiative transport moves energy through repeated absorption, emission, and scattering of photons. A photon may travel only a short distance before interacting with matter. Another photon is then emitted, perhaps in a different direction and with a different energy. The overall flow moves outward because the interior is hotter than the layers above it. Calling this a flow of photons can create the impression of light streaming through a clear room. It is closer to a very long random walk through a packed building. Progress is made, but not with confidence or in a straight line. The energy may take many interactions to reach the outer layers. Whether convection or radiation dominates depends on how quickly temperature changes with depth, how opaque the gas is, and how easily rising material can continue moving. Stellar models calculate the temperature gradient that radiation would require. If that gradient becomes too steep, the gas becomes unstable to convection, and physical motion begins carrying part of the energy instead. A growing dark star may therefore change its internal organization. It can begin with a structure that is strongly convective and gradually develop larger radiative regions as its mass increases. The transition would not divide the object into permanently fixed zones. The boundaries could move while the star accreted material and adjusted to changes in its heating rate. Radiation pressure also becomes increasingly important in a very massive object. Gas pressure comes from the motion and collisions of particles. Radiation pressure comes from photons transferring momentum as they are absorbed or scattered. At modest stellar masses, gas pressure can provide much of the support. In an extremely massive star, the intense radiation field can contribute a significant fraction. Photons do not weigh anything in the ordinary resting sense, but they carry energy and momentum. When they interact with matter, they exert force. Deep inside a luminous star, the accumulated radiation pressure can help hold the outer layers against gravity. This creates another balance. More mass produces stronger gravity, but it also allows the star to generate and contain more radiation. The luminosity cannot rise without limit while the outer gas remains securely bound. At sufficiently high luminosity, the outward force of radiation on the material approaches the inward pull of gravity. Astronomers describe the corresponding level as the Eddington luminosity. The Eddington luminosity depends mainly on the star's mass and on how strongly its material interacts with radiation. A star near that limit does not automatically explode. It means radiation pressure has become an important part of the force balance, especially in the outer layers. Continued accretion, atmospheric motion, and mass loss become more sensitive to the details of opacity and geometry. Dark stars can become extremely luminous while remaining near or below this limit in theoretical models. Their large radius helps because the same total luminosity is spread over a vast surface. Each square meter of that surface emits less energy than it would on a smaller, hotter star. This brings us to the meaning of cool. A dark star described as cool may have an effective surface temperature between roughly 4,000 and 10,000 Kelvin. In many early calculations, nothing at that temperature is cool by human standards. A person approaching the photosphere would not experience mild cardigan weather. The description is comparative. Ordinary massive population 3 stars are expected to be much hotter at the surface. A compact metal-free star with a very large mass can reach effective temperatures of many tens of thousands of Kelvin. It releases a substantial amount of its energy as ultraviolet radiation. A dark star with a surface temperature nearer 10,000 Kelvin is cool beside such an object, even though it remains hotter than the surface of the Sun in some models. The effective temperature is not necessarily the temperature of one sharply defined layer. It is the temperature a perfect thermal emitter would need in order to release the same total energy per unit surface area. Real stellar atmospheres absorb and emit different wavelengths with different efficiencies, so the observed spectrum contains more information than a single temperature. The relation between luminosity, radius, and temperature explains how a cooler object can be astonishingly bright. The total luminosity rises with the surface area and with the fourth power of the effective temperature. A lower temperature reduces the power emitted by each unit of area. A much larger radius increases the number of emitting units. Consider 2 electric heating elements. One is extremely hot but small. The other is cooler but covers the walls, floor, and ceiling of an entire building. The smaller element can have the higher temperature, while the larger one releases more total energy. A dark star applies that principle with slightly more hydrogen and a considerably less cooperative electricity bill. A radius of around 10 astronomical units appears in many dark star models, although the exact value changes with mass, dark matter properties, and accretion history. 10 astronomical units would extend from the Sun beyond the orbit of Saturn. Some configurations could be smaller, and very massive versions could reach different sizes, but the central idea remains that these objects are enormous compared with conventional stars. The Sun's radius is less than 1/100th of the distance between Earth and the Sun. A dark star several astronomical units wide would therefore have a radius hundreds or thousands of times greater than the Sun's. It could contain hundreds of solar masses while maintaining a surface temperature in the same broad range as much less massive visible stars. From a distance, the surface would not look dark. It would glow. At temperatures of several thousand Kelvin, much of the radiation would emerge in visible and infrared wavelengths, although cosmic expansion would later stretch the light from an early dark star towards still longer wavelengths before it reached modern telescopes. Its appearance would depend on temperature. At the cooler end of the predicted range, the star could appear reddish by stellar standards. At the hotter end, it would appear whiter or bluer. No human eye would have been nearby to enjoy the distinction, and placing one there would introduce several practical problems, beginning with the absence of a suitable viewing platform. The atmosphere would be made almost entirely from hydrogen and helium. Heavy elements would be absent unless the star formed after nearby stellar explosions had already enriched the gas, which would no longer represent the simplest first-generation case. There would be no iron, calcium, carbon, or oxygen lines in the proportion seen in later stars. Hydrogen would dominate many of the spectral features. Depending on the temperature and density of the atmosphere, atomic hydrogen could absorb or emit light at characteristic wavelengths. Cooler models might also allow signatures involving molecular hydrogen. Helium lines could appear under suitable conditions, although exciting helium strongly requires enough energetic radiation. Predicting the exact spectrum requires more than knowing the effective temperature. Surface gravity affects the pressure and width of absorption lines. The motion of the atmosphere can shift or broaden them. Gas falling onto the star may create shocks and additional radiation. Material around the object can absorb its light, reprocess it, or produce emission of its own. The dark star could therefore be surrounded by a complex envelope. Accreting gas would continue arriving from the primordial cloud. Some of it might form a disk because even a small amount of rotation prevents matter from falling directly inward. Gas in the disk would gradually lose angular momentum and move toward the star. The outer atmosphere and the inner accretion flow could interact. Radiation from the star would heat the incoming gas. Accretion shocks could heat material where it joined the stellar surface. The large stellar radius changes the energy released by this process, because gas falling onto a broad object does not travel as deeply into a gravitational well as it would before reaching a compact star. For the same mass, a smaller star gives infalling gas more distance over which to accelerate and releases more gravitational energy per unit mass at the surface. A puffy dark star spreads its mass through a larger radius, reducing the surface gravitational potential compared with a compact star of equal mass. Accretion is still energetic, but it may be less violent at the surface than it would be on a small, dense object. Surface gravity would also influence the atmosphere. A large radius reduces the gravitational acceleration at the visible edge. The atmosphere could be extended, with pressure falling gradually rather than over a thin layer. That makes the word surface even less precise. There is no place where one could tap the star and hear a reassuring solid sound. Despite the lower surface gravity, the escape speed can remain high because the total mass is so large. Surface gravity describes the local acceleration, while escape speed depends on the total energy required to leave the gravitational field. A massive extended object can have a gentle-looking outer gradient and still be very difficult to escape. The outer layers might also move. Convection can reach near the photosphere. Radiation pressure can produce pulsations or instabilities. Accretion adds material unevenly. A dark star should not be imagined as a perfectly still sphere with every atom holding a permanent assigned position. Stellar equilibrium means that the large-scale structure changes slowly, compared with the time required for pressure forces to respond. It does not mean nothing moves. The Sun is in equilibrium while containing convection, waves, rotation, magnetic fields, and occasional behavior that interferes with radio communication. A dark star could be stable overall while remaining active inside. Rotation introduces another complication. The primordial gas cloud would almost certainly carry some angular momentum. As it contracted, rotation would become faster, much as a skater spins faster when drawing in their arms. The dark star could therefore rotate, and the surrounding gas would likely form a disk. Fast rotation can flatten a star slightly, making its equator wider than its poles. It reduces the effective inward pull at the equator and changes how gas accretes. In the most rapidly rotating models, it may affect how large the star can grow before material is shed or accretion is redirected. Simplified stellar calculations often begin with spherical symmetry because it makes the equations manageable, but real objects are not required to respect the convenience of the calculation. Magnetic fields are another uncertain ingredient. Primordial gas could contain weak seed fields that were amplified during collapse and accretion. Magnetic forces might influence the disk, move angular momentum, or help launch outflows. Dark star models often focus first on gravity, radiation, gas pressure, and dark matter heating because those are the essential parts of the proposal. Adding rotation and magnetic fields makes an already difficult problem even more cheerful. The internal dark matter component would remain small throughout this broad structure. It would not contribute much to the pressure directly. Ordinary gas and radiation would provide the support. Dark matter would contribute energy, and its gravity would be minor compared with the gravity of the star's hydrogen and helium once the object became massive. This is worth separating carefully. Dark matter helps create the halo where the star forms. A concentrated portion provides the annihilation fuel, yet the star's own gravitational field is eventually dominated by ordinary matter. The dark matter acts more like a compact energy supply than a structural framework. As annihilations continue, the fuel distribution changes. The particles nearest the center, where annihilation is fastest, are consumed most quickly. That could flatten the central dark matter profile over time. New particles on passing orbits may enter the region, and gravitational changes caused by continued accretion may draw more inward. The internal heating pattern therefore evolves along with the star. If the supply declined gradually, the star would begin contracting. Its radius would shrink and the central temperature would rise. The surface temperature could increase as well. Fusion would become more important. On a diagram of stellar luminosity and temperature, the object would move away from the cool, inflated region and toward the position expected for a conventional massive star. If fresh dark matter were captured efficiently, the inflated state could last much longer. The star might remain cool and broad even after the initial gravitationally concentrated reservoir had been used. The possible lifetime ranges widely because it depends on dark matter density, scattering properties, orbital structure, and the continuing supply of ordinary gas. That uncertainty does not prevent us from understanding the physical picture. The puffy structure is the star's response to receiving energy before it contracts enough for normal fusion to dominate. The extra heat raises the pressure. Increased pressure expands the gas. Expansion lowers the density and temperature. The lower surface temperature weakens the ionizing radiation that would otherwise interrupt accretion. The star's size is therefore connected directly to its future mass. It is not merely a strange result produced by an unusual heat source. By remaining large and comparatively cool, the object changes the environment around itself. It does not sterilize the surrounding cloud as quickly as an ordinary massive population 3-star might. Gas can continue approaching through the halo and the accretion disk. A conventional massive star begins fighting its own growth as it becomes hotter and brighter. Ultraviolet radiation ionizes the nearby gas. Heated gas expands. Radiation pressure acts on electrons, atoms, and any available opacity. outflows can remove material. The star becomes increasingly effective at closing the kitchen while still asking for dinner. A dark star is also luminous, but its cooler spectrum produces fewer photons energetic enough to ionize hydrogen. Much of its power emerges at longer wavelengths. The total energy output can be enormous without creating the same immediate ionized region around the star. That gives incoming material more time to reach the surface. Its broad radius also changes the accretion geometry and the amount of energy released when gas arrives. The surrounding disk can feed the star, while the interior continuously readjusts. Added mass strengthens gravity. The structure contracts slightly. Dark matter heating responds. Pressure rises, and the star expands into a new equilibrium. Repeated many times, that process can carry the object far beyond its original mass. The cool, puffy giant is not a fixed object waiting in one state. It is an evolving stellar structure designed by the balance between dark matter, heating, gravity, radiation, and a continuing supply of primordial gas. Once that supply begins arriving faster than the star can significantly alter its surroundings, the central question changes. How does a dark star remain so large? How can the same inflated structure allow it to accumulate hundreds, thousands, or even far more solar masses without ordinary stellar feedback stopping the process? The answer begins with a process that sounds ordinary by astronomical standards. The star grows because gas falls onto it. Dark matter supplies the unusual heating, but almost all of the added mass is ordinary hydrogen and helium drawn from the surrounding halo. A dark star does not become enormous by swallowing a mountain of dark matter. It becomes enormous by remaining in a condition that allows it to keep accepting normal gas long after an ordinary massive star would have begun pushing that gas away. The material outside the star is already moving inward. It has cooled, lost energy, and settled toward the center of the dark matter halo. Some of it falls almost directly. Some carries enough angular momentum to form a rotating disk. Streams can arrive from different directions, shocks can heat the gas, and clumps may form within the flow. The overall result is a continuing delivery system, although it is less like a smooth pipe and more like a crowded roundabout designed by gravity. Accretion adds mass one parcel at a time. Gas in a disk must lose angular momentum before it can move closer to the star. Friction, turbulence, gravitational torques, and magnetic effects can transfer that angular momentum outward. Material nearer the center then spirals inward and eventually joins the stellar surface. Each addition deepens the gravitational field and forces the star to find a new balance between pressure, radiation, and the heating supplied by dark matter annihilation. The rate of growth depends on the surrounding cloud. If the star gains 1,000th of a solar mass each year, reaching 100,000 solar masses would take roughly 100 million years if the rate remained steady. At 100th of a solar mass per year, the same increase would take about 10 million years. Higher rates shorten the schedule, while interruptions, fragmentation and feedback lengthen it or stop it altogether. The important point is that supermassive growth is not one dramatic meal. It is a long sequence of ordinary deliveries. A conventional population 3 protostar can also accrete quickly at first. The difference appears when it contracts. As a normal protostar gains mass, gravity compresses it. The central temperature rises, nuclear burning becomes important, and the surface grows hotter. A hot, massive star produces large numbers of ultraviolet photons, energetic enough to ionize hydrogen. Those photons change the gas around the star and eventually make further growth much more difficult. Ionization removes an electron from a hydrogen atom. The newly ionized gas is heated, and hot gas has greater pressure than cold gas. An expanding region of ionized hydrogen can form around the star. If that region breaks out of the dense accretion flow, it can drive material away, erode the disk, and reduce the supply reaching the surface. Radiation pressure and photoevaporation add to the problem. the growing star begins to interfere with its own food source. This feedback is particularly strong because the number of ionizing photons depends sharply on surface temperature. Two stars can have similar total luminosities while producing very different amounts of ionizing radiation. A cooler star releases more of its energy at longer wavelengths. A hotter star shifts a larger fraction into ultraviolet light. The distinction is rather like comparing two lamps that use the same amount of power, except one fills a room with comfortable visible light and the other is designed to remove electrons from the wallpaper. The inflated dark star remains on the cooler side of that comparison. Its enormous surface area allows it to radiate a tremendous amount of energy without becoming as hot at the photosphere as a compact star of the same mass. Dark matter heating keeps the interior from contracting deeply, so the effective temperature can remain below the level where hydrogen ionizing output becomes overwhelming. The star shines intensely, but much of that light is not energetic enough to create the same destructive feedback around it. That difference gives accretion more time. Gas continues flowing through the halo and disk because the star has not yet produced a large, expanding ionized bubble capable of clearing the central region. The incoming material may be heated and disturbed, but it is not necessarily expelled. The star can therefore pass masses that would be difficult for an ordinary first-generation star to reach under similar conditions. The effect is not simply that a dark star is dimmer. It may be millions or billions of times as luminous as the Sun. What matters is the spectrum of that luminosity. Total brightness measures the amount of energy leaving each second. Feedback depends on how that energy is distributed among different wavelengths and how those photons interact with the surrounding gas. A very bright but relatively cool star can be less effective at ionizing hydrogen than a smaller, hotter object. As more gas arrives, the dark star does not keep exactly the same radius, density, or internal temperature. The added weight encourages contraction. Contraction raises the dark matter density in the region occupied by the star and can increase the annihilation heating. The extra energy raises the pressure and expands the stellar envelope. The object settles into another equilibrium with a greater mass. Stellar models can follow this process as a sequence. Begin with a small hydrostatic dark star. Add a modest amount of hydrogen and helium. Recalculate the gravitational field, pressure profile, temperature, dark matter distribution, and luminosity. Allow the object to relax. Then add more gas and repeat. After enough steps, the calculation traces a path from a star of roughly solar mass to one containing hundreds, thousands, or far more solar masses. The ordinary matter is doing nearly all of the growing. The dark matter component remains tiny by mass, yet it must continue supplying enough energy to hold the enlarged star in its inflated state. This creates a fuel problem. A larger star radiates more power. Greater luminosity requires a higher annihilation rate or another energy source. The dark matter reservoir must therefore be replenished or rearranged as the object grows. One proposed source is continued gravitational contraction of the halo. Gas falling into the center changes the gravitational potential, pulling some dark matter orbits inward. Many of those orbits are not circular. A particle can spend most of its time far from the star and still pass through the central region during each orbit. That matters because the supply is not limited to dark matter, sitting permanently inside the photosphere. Particles on elongated paths can repeatedly cross the dense interior, where annihilations are most likely. The available population of such orbits is not endless. Every annihilation removes two particles. Over time, trajectories that regularly pass through the center can be depleted. The halo may rearrange and send new particles inward, but the rate depends on its shape, its mergers, and the way ordinary matter accumulates. A perfectly spherical, unchanging model is easier to calculate than a real halo filled with moving gas, clumps, and neighboring structures. Non-spherical halos may sometimes help. In a spherical gravitational system, particle orbits conserve quantities that can keep much of the dark matter away from the center. In a triaxial or irregular halo, a larger family of orbits can wander through the central region. Those paths may refill the population available for annihilation and extend the dark-powered phase. Halo mergers can also add material and disturb the orbital structure. The same disturbances can cause trouble. A merger might move the dark star away from the point of highest dark matter density. A second protostar could tug it out of the central cusp. Fragmentation in the disk could create companions that compete for gas. An event that supplies more fuel on one scale may remove the star from its best fuel source on another. Cosmic growth rarely offers a benefit without attaching several conditions in smaller print. Capture provides a second possible route for replenishing dark matter. A particle passing through the star may scatter from a hydrogen or helium nucleus. Most particles would continue on their way without noticing that a star had been placed in the path. If one loses enough kinetic energy in a collision, however, the star's gravity can trap it. Repeated passages and further scattering allow the particle to settle into the central region, where it may annihilate with another captured particle. The capture rate depends on several uncertain quantities. The surrounding dark matter density must be high enough. The particles must scatter from ordinary nuclei often enough to be trapped. The star must remain near the dense centre of the halo. Direct detection experiments place limits on these interactions, but they have not established the properties needed to calculate a definite capture rate for an early dark star. If capture is efficient, the star can maintain dark matter heating for much longer than the initial contracted reservoir would allow. It can continue accreting while remaining inflated. If capture is weak, the annihilation supply may decline, the object may contract, and ordinary stellar feedback may begin before it reaches a supermassive scale. The enormous versions of dark stars therefore belong to the part of the theory where refueling works well enough and the gas supply continues. The halo itself sets a basic limit. A star cannot accrete more ordinary matter than its environment contains. A small mini-halo may hold a total mass of around 1 million suns, but only a fraction of that is baryonic matter, and only part of the baryonic material reaches the centre. Some remains hot, some carries too much angular momentum, some forms other objects, and some may be driven away. Even a very successful central star cannot send an invoice to the universe for gas that is not there. Growth to 100,000 or 1 million solar masses is easier to imagine in a larger halo or in a halo that gains material through mergers. As the host system grows, fresh gas can flow toward its centre. The dark star may then receive a supply far beyond the contents of the original mini-halo. Theoretical models have explored objects above 100,000 solar masses and, under generous assumptions, around 1 million solar masses or more. These numbers should not be treated as a standard expected mass. They describe possible outcomes within models. A dark star of several hundred solar masses, one of several thousand, and one of 1 million all require different amounts of gas, time, and dark matter support. The phrase supermassive dark star usually refers to the high end, commonly above about 100,000 solar masses, where the object begins to overlap in mass with the lighter range of massive black hole seeds. At those masses, luminosity becomes extraordinary. A supermassive dark star could shine with billions or tens of billions of times the luminosity of the Sun. Its brightness would rise roughly with its mass, because a radiation-supported star tends to remain near a fixed fraction of the Eddington limit. The object could be visible across a large fraction of the observable universe in principle, provided it existed in sufficient numbers and its ancient light could be separated from galaxies and accreting black holes. Radiation pressure is an obvious obstacle. As luminosity rises, photons push outward on the stellar gas and on the infalling material. Near the Eddington limit, the outward force associated with radiation can rival gravity for material with the relevant opacity. This sounds as though growth should stop automatically, but the result depends on geometry, wavelength, and where the radiation is absorbed. Accretion through a disk is not the same as spherical gas falling evenly from every direction. Radiation may escape more easily along the poles, while dense material continues entering near the equatorial plane. The outer atmosphere can expand and adjust. The star can remain near the Eddington limit without immediately throwing away all of its mass. Massive stars are capable of living close to that boundary, although they become increasingly sensitive to pulsations, rotation, and mass loss. Dark matter heating helps here indirectly. By keeping the surface cooler, it changes the opacity and reduces the ionizing photon supply that would heat the surrounding gas. The radiation still carries momentum, but it does not interact with every part of the inflow in the same way. A cool, extended star can therefore remain luminous, while allowing disk-fed accretion to continue. Rotation adds another boundary. Gas arriving through a disk carries angular momentum, and some of it is transferred to the star. If the stellar surface rotates too quickly, material near the equator approaches the speed needed to escape. Further accretion then requires angular momentum to be removed through the disk, magnetic fields, gravitational torques, or outflows. A growing dark star cannot simply store unlimited spin, any more than a cupboard can accept unlimited plates, because the door is technically still open. The large radius helps to some extent. A broad star can hold more angular momentum without rotating as quickly as a compact one, just as a skater slows by extending their arms. Yet the object may contract or expand during growth, changing its rotation rate. Detailed three-dimensional evolution is more complicated than a spherical model, and rotation could reduce the maximum mass in some environments. Fragmentation may be even more important. The accretion disk can become gravitationally unstable and break into clumps. Some clumps spiral inward and merge with the central star. Others survive as companions. A group of protostars then shares the available gas. The central object grows more slowly, and gravitational encounters may move it away from the densest dark matter region. On the other hand, fragments do not always prevent a massive central object. They can migrate inward, collide, or be tidally disrupted. A disk can deliver gas in bursts rather than at a steady rate. The final result depends on cooling, turbulence, magnetic fields, and the speed at which material is supplied from larger scales. This is one reason simplified accretion histories should be understood as controlled experiments, rather than complete recordings of what the first halos did. The newer stellar evolution calculations reinforce that sensitivity. Models with weaker dark matter heating contract become hotter and eventually produce enough radiative feedback to stop growth at several hundred solar masses. Models placed in denser dark matter environments remain expanded, emit far fewer ionizing photons, and can continue accreting toward 100,000 solar masses in the calculation. A small change in the invisible environment can therefore produce a large change in the final stellar mass. The time required also affects whether the environment remains favourable. A star growing at 1/100th of a solar mass per year needs about 10 million years to add 100,000 solar masses. During that interval, the host halo evolves. Nearby stars may form. Supernovae may enrich or disturb the gas. External radiation can alter molecular cooling. Mergers can add material or disrupt the central structure. The dark star must not only receive fuel, it must remain in the right place while the universe changes around it. If the conditions cooperate, the growth can become self-reinforcing for a while. More mass deepens the gravitational potential and helps draw gas inward. Continued dark matter heating keeps the star broad. The broad star stays comparatively cool. The cooler spectrum limits ionizing feedback. Weak feedback allows more gas to arrive. That gas increases the mass and deepens the potential again. This loop does not violate any limit by itself. It simply delays the feedback that normally ends rapid stellar accretion. Eventually another limit must intervene. The gas reservoir can be exhausted. The inflow can slow. The star can move away from the dark matter cusp. Dark matter particles can be consumed faster than they are replaced. Rotational radiation can remove material. the object can encounter a relativistic instability at very high mass. No star receives an exemption from physics merely because its heating system is unusual. Still, delaying ordinary feedback has major consequences. A normal first star may leave a black hole with tens or hundreds of solar masses, depending on its evolution. A supermassive dark star could leave a remnant containing a substantial fraction of 100,000 or 1 million solar masses. That difference changes the later problem of building the first quasars. A heavy seed begins much closer to the required mass and needs fewer periods of rapid accretion after collapse. Before collapse occurs, the growing star remains an extended object rather than a black hole. Its radius may span many astronomical units. Its centre can remain cooler and less dense than the centre of an ordinary compact star of equal mass. Radiation pressure carries much of the structural load. Dark matter annihilation continues replacing the energy lost from the surface. Hydrogen remains abundant because fusion is not consuming it at the rate expected in a conventional massive star. The enormous mass therefore accumulates without the usual nuclear clock advancing in the usual way. The star can spend much of its growth outside the standard sequence of stellar evolution. Its age, mass, and fuel consumption no longer have the familiar relationship. A million solar mass object might still be supported mainly by a dark matter component representing only a tiny part of its total mass. That arrangement becomes harder to maintain as the luminosity rises. A more massive star loses energy from its surface at a greater rate, so the furnace must provide more power. The central dark matter population is steadily being removed by annihilation. If capture or orbital replenishment keeps pace, the inflated state continues. If it falls behind, the star begins using gravitational contraction to cover the difference. At first, the shortage would not look dramatic. The star would still be enormous, luminous, and apparently stable. Gas would still move through its outer layers. Radiation would still leave the photosphere. The surrounding halo might continue feeding material towards the center. What would change is the balance hidden inside. Each second, the star would radiate energy into space, and the dark matter annihilations would replace a slightly smaller fraction of it than before. That small deficit matters because a star cannot ignore its energy budget for long. If the interior loses more energy than its power source provides, pressure begins to fall. Gravity then pulls the gas inward. The contraction is not a sudden collapse. It is a controlled adjustment, with each layer settling to a slightly smaller radius, while the whole structure searches for a new equilibrium. Dark matter annihilation may continue throughout this process. The fuel does not vanish in one instant. Particles on orbits crossing the star keep passing through the dense interior, and some still meet and annihilate. The problem is that the reservoir is being consumed while the star's demand remains high. A supermassive object radiates an extraordinary amount of energy. Supporting it requires a continuing supply, not merely a few remaining particles making a brave effort near the center. The rate of replenishment can fall for several reasons. The dark matter brought inward during the star's formation may already have been heavily depleted. Orbits that repeatedly cross the stellar interior are the most useful for heating, but they are also the ones whose particles are most likely to annihilate or scatter. Dark matter farther out in the halo may remain abundant while travelling on paths that never enter the star. A full pantry is not very helpful when the only food left is stored in a locked building across town. Capture through scattering may also weaken. For capture to work, a dark matter particle must pass through the star, collide with an atomic nucleus, lose enough energy, and remain gravitationally bound. Repeated interactions can then draw it toward the centre. Most particles do not scatter at all. Those that never cross the star cannot be captured by it, no matter how much dark matter exists elsewhere in the halo. One detailed study of first-generation dark stars found that the population on star-crossing orbits could be depleted rapidly, while much of the remaining dark matter stayed nearby on orbits that did not enter the stellar body. In that model, capture could not keep the first dark star phase operating indefinitely. The result depends on assumptions about the halo and particle interactions, but it illustrates the central problem. The amount of dark matter near a star is not the same as the amount available to fuel it. As the annihilation luminosity falls, the star begins contracting under gravity. This contraction releases energy. Gas falling inward gains speed, particles collide more often, and gravitational potential energy is converted into heat. The star temporarily replaces part of the missing dark matter power with the energy of its own shrinking structure. This stage is related to Kelvin-Helmholtz contraction, the process that powers an ordinary protostar before sustained nuclear fusion begins. A contracting object can shine because gravity supplies energy as its material settles inward. The star is effectively paying its energy bill by becoming smaller. That arrangement cannot continue forever. There is only a limited amount of gravitational energy available between one stable size and the next. Continued radiation requires continued contraction, and continued contraction raises the central temperature. The inflated dark star begins moving away from the cool, broad configuration that allowed it to grow so efficiently. The center responds first. It supports the greatest weight and reaches the highest density. As the star shrinks, pressure rises, particles move faster, and collisions become more energetic. The outer layers also contract, but the central temperature changes most dramatically. A star that once avoided normal fusion by remaining expanded now approaches the conditions needed for nuclear reactions. The contraction can briefly increase the dark matter heating. Compressing the star may concentrate the remaining particles and raise the annihilation rate. Since annihilation depends strongly on density, a smaller volume can make the last accessible fuel burn more rapidly. This may slow the contraction for a time, producing a period in which the star adjusts through several near equilibrium states, rather than moving smoothly in one direction. There is a slightly inconvenient consequence. Concentrating the remaining fuel makes it more useful in the short term and removes it faster in the long term. It is similar to turning up the final radiator in a cold house. The room warms, but the meter becomes noticeably more enthusiastic. Eventually, the nuclear reactions inside ordinary matter become important. The exact sequence depends on the star's mass, composition, and previous evolution. The gas began with almost no elements heavier than helium, so it does not start with the same mixture found in the Sun. Hydrogen burning can begin through reactions that require only hydrogen, while higher central temperatures and the first production of small amounts of carbon can allow more temperature-sensitive reaction cycles to contribute. Zero metallicity stellar models show that the creation of trace carbon can change the dominant route of hydrogen burning, especially in massive stars. The crucial point is not the name of every reaction. It is that the star has acquired a new internal power source. Hydrogen nuclei combine through a chain of reactions. A small fraction of their mass becomes energy, and the resulting heat begins supporting the star. The object that was once powered mainly by dark matter annihilation starts behaving more like an ordinary massive star. There may not be one clean moment when the first source turns off and the second turns on. Dark matter heating, gravitational contraction, deuterium burning, and hydrogen fusion can overlap. Their relative contributions change over time. At one stage, annihilation dominates. Later, contraction supplies much of the missing energy. Fusion then grows until it provides most of the luminosity. This overlap is important because a star reacts to the total heating, not to the label attached to each contribution. If fusion begins while annihilation still supplies a noticeable amount of power, the star may contract more slowly. If the dark matter supply drops sharply, nuclear burning must rise more quickly to establish equilibrium. Different fuel histories can therefore produce different paths toward the main sequence. The phrase main sequence refers to the long period when a star is supported mainly by hydrogen fusion in its core. For a dark star that has already accumulated hundreds, thousands, or perhaps hundreds of thousands of solar masses, arriving there would be a very unusual event. It would not be a small protostar settling calmly into a familiar adulthood. It would be an enormous object switching to a power source whose consequences it had postponed during its growth. One immediate consequence is a rise in surface temperature. As the star contracts, the same or greater luminosity escapes through a smaller surface area. The effective temperature increases. The spectrum shifts towards shorter wavelengths, producing more ultraviolet radiation. Photons energetic enough to ionize hydrogen become much more numerous. Recent stellar evolution calculations of dark matter-heated population 3 protostars find this transition clearly. In those models, depletion of the dark matter fuel allows contraction and core burning, while the ionizing photon output can rise to around 10 to the 53 photons per second in the most extreme cases. The exact value is model dependent, but the direction is robust. A compact fusion-powered object is far more effective at ionizing its surroundings than the earlier inflated star. The change would transform the environment around the star. Neutral hydrogen close to the surface absorbs ionizing photons and loses electrons. The gas becomes hotter. Hot ionized gas expands, increasing pressure against the material still trying to fall inward. An ionized bubble may begin forming around the star, first trapped by dense accretion flows and later pushing into the surrounding halo. Accretion through a disk may continue for a while. Dense material near the equatorial plane can shield itself more effectively than gas in other directions. Radiation may escape along lower density routes near the poles. The flow becomes uneven, with some regions still feeding the star while others are heated and cleared. As the ultraviolet output rises, however, the conditions that allowed exceptional growth begin to disappear. The disk can be photo-evaporated from its exposed surfaces. Gas farther out is heated before it reaches the center. Radiation pressure adds outward momentum. The star begins closing the route by which most of its mass arrived. This creates a sharp contrast with the earlier phase. While dark matter heating kept the star cool, brightness did not automatically end accretion. Once contraction raises the surface temperature, the same enormous luminosity becomes much more effective at disrupting the surrounding gas. The star's energy has not merely increased, it has changed into a form that the environment absorbs more efficiently. The final mass may therefore depend on the timing of fuel depletion. A dark star that loses its annihilation support at several hundred solar masses could enter fusion while a substantial gas reservoir remains around it. Strong feedback might halt growth near that scale. Another object that remains dark matter-powered until it reaches 100,000 solar masses would begin the same transition with a vastly greater mass already secured. The halo also matters. Dense inflows can resist feedback longer than thin ones. A larger halo can confine heated gas more effectively. Rapid accretion can bury radiation and keep the star inflated through ordinary accretion energy even after dark matter heating weakens. Rotation, disk structure, nearby stars and mergers all affect how quickly the new ultraviolet source clears its surroundings. For this reason, the fading of dark fuel is not a universal clock that rings at one fixed age. It is an environmental event. The star reaches it when its rate of dark matter consumption exceeds the rate at which useful particles are supplied. One object may reach that point early. Another may remain supported for millions of years. A model with efficient capture or replenishment may extend the dark phase much longer, while a model with a depleted set of central orbits may end it comparatively quickly. The star's appearance would change during the transition. The broad, cooler photosphere would shrink. The color temperature would rise. The spectrum would gain stronger signatures of ionized gas, both in the stellar atmosphere and in the surrounding region. Radiation absorbed by nearby hydrogen could be re-emitted at characteristic wavelengths, creating a bright nebular component around the star. An observer at great distance might therefore see different stages as different kinds of source. The inflated phase could resemble a very luminous, relatively cool stellar object. The contracting phase could move through a rapidly changing temperature range. The fusion-powered phase could appear hotter and be surrounded by strong ionized emission. Separating these possibilities from compact galaxies or accreting black holes would remain difficult, but the transition itself offers possible clues. Inside, the structure changes just as substantially. Radiation pressure may already provide much of the support in a supermassive dark star. As the object contracts and heats, nuclear energy generation becomes concentrated in the central region. Convection can develop or shift as the temperature gradient changes. The star may build a distinct burning core while retaining a massive envelope. The core is not necessarily quiet. Nuclear reaction rates can be extremely sensitive to temperature. A small contraction raises the temperature and can increase the energy production sharply. Expansion then cools the core and slows the reactions. This feedback can stabilize burning, but very massive stars operate close to limits, where radiation pressure, relativistic gravity, and dynamical instabilities become increasingly important. Pulsations may appear. Layers can expand and contract in repeating cycles if heating, opacity, and pressure respond with the right timing. Some pulsations remain modest. Others can drive mass loss from the surface. Predicting this behavior requires detailed models because an extended primordial star has little heavy element opacity, unusual internal heating history, and a mass far beyond most stars observed nearby. Mass loss at zero metallicity may be weaker through some mechanisms because metals provide many spectral lines that absorb radiation and help drive stellar winds. That does not mean a primordial supermassive star loses no mass. Electron scattering, continuum radiation pressure, pulsations, rotation, and violent instabilities can still remove material. The amount lost before collapse is one of the uncertainties that determines the mass of the eventual remnant. The fusion phase may be surprisingly brief compared with the dark-powered growth. A dark star could spend a long time accreting while using only a small amount of its hydrogen. When the dark fuel fades, it enters nuclear burning with a huge mass and a very high luminosity. Massive stars consume fuel rapidly because the power they radiate rises steeply with their mass, even though the available hydrogen is also larger. A supermassive star does not gain a proportionally long life merely by having more fuel. It also has a much larger appetite. If a small car and a cargo aircraft both begin with full tanks, the aircraft does not necessarily travel for more hours. It has brought more fuel and found a remarkably efficient way to use it quickly. Older dark star calculations often describe the post-dark phase as a very massive zero-metallicity main sequence star that later collapses into a black hole. Supermassive dark star models likewise find that once the annihilation supply ends, the object shrinks, heats, begins fusion, and rapidly loses the cool conditions that permitted continued accretion. At the highest masses, another path may interrupt the ordinary sequence. The star can become unstable because Newtonian gravity is no longer an adequate approximation. General relativity slightly strengthens the tendency toward collapse. In an ordinary star, the correction is tiny. In an object containing tens of thousands, hundreds of thousands, or millions of solar masses, supported largely by radiation pressure, that correction can become decisive. Radiation pressure has an equation of state that is only just stiff enough to support a very massive star under Newtonian gravity. The gas behaves close to a critical balance. General relativistic effects tip that balance by making gravity effectively stronger in the dense central region. Once the star crosses the stability boundary, a small contraction does not produce enough additional pressure to restore equilibrium. Dark matter heating can delay or alter that instability by keeping the star larger and less centrally compressed. A strong continuing heat source maintains a broad configuration. As the fuel fades and the star contracts, it may move closer to the relativistic limit. The same loss of support that starts fusion can therefore prepare the object for a much more rapid collapse later. The exact order depends on mass and dark matter density. Some models allow a star to remain dark matter supported beyond 1 million solar masses if the ambient density stays high. At lower dark matter densities, calculations find contraction and instability at lower masses. A recent analysis proposes that accreting dark stars can encounter general relativistic instability across a broad range from roughly 10,000 to 10 million solar masses, although this is a developing theoretical result rather than a confirmed evolutionary track. Before instability becomes dynamical, the star may still pass through a period of nuclear burning. Hydrogen fusion can temporarily replace the missing annihilation power. The photosphere heats, accretion weakens, and the core evolves. If the star is below the relativistic threshold, it may follow a more recognizable massive star life, progressing to heavier nuclear fuels as the core composition changes. If it is already too massive, nuclear burning may not provide a long rescue. The star's center can contract faster than pressure adjusts. Temperatures soar. Neutrino losses may become important. Rotation can slow collapse in some directions and create a disk. Magnetic fields can be amplified. The object begins moving from stellar evolution into relativistic collapse. There is no need for the dark matter to disappear completely before this happens. A small population may remain inside or around the star. It simply no longer supplies enough energy to control the structure. At that point, calling the object a dark star becomes less useful. The defining feature was that dark matter annihilation dominated its power. Once fusion, contraction, or relativistic infall takes over, the star has entered another state. The remaining dark matter may still affect the surroundings. Particles that survive outside the contracting object can form a dense envelope or spike around the eventual remnant. Later annihilations might produce radiation, and the distribution could influence hypothetical observational signals. Those effects are secondary to the immediate change inside the star, where ordinary matter now determines the outcome. The fading fuel therefore does more than switch off a heater. It removes the condition that kept an extraordinary mass spread across an extraordinary radius. Gravity regains control of the scale. The star contracts. Nuclear reactions begin. Its light becomes harder, and the gas supply that built it is exposed to intense feedback. For a lower mass dark star, this may lead to a brief but recognizable life as an unusually massive population 3-star. For a supermassive one, the interval may be much shorter and less stable. The center is already carrying the weight of an object large enough to test the distinction between an enormous star and a forming black hole. As the radius continues to shrink, escape speeds rise, the internal clock accelerates, and the star approaches the point where pressure can no longer arrange a new equilibrium. Can any signal, force, or nuclear reaction prevent the entire object from falling inward? Pressure can resist gravity only while the star is able to increase that pressure when its center is compressed. During most of the dark-powered phase, heating from annihilation helps the gas respond. Later, fusion and the release of gravitational energy may do the same. In an extremely massive object supported mainly by radiation pressure, however, the margin becomes very narrow. A small inward movement strengthens gravity, and beyond a critical point, the resulting rise in pressure is no longer enough to reverse the contraction. This is the general relativistic instability. It does not mean that gravity suddenly changes its rules. General relativity has been present throughout the star's life. The corrections were simply too small to control the earlier structure. As the central region becomes more compact and the escape speed rises, those corrections matter more. Newtonian calculations begin to underestimate how strongly the mass curves space-time, and the star crosses from a condition that can recover after a disturbance into one that cannot. The first movement inward may still look like ordinary contraction. Central density rises, the temperature climbs, nuclear reactions accelerate. Some layers briefly gain pressure, and the star may hesitate. Depending on its mass and composition, nuclear burning can alter the details, and certain supermassive star models even allow violent thermonuclear outcomes rather than a quiet direct collapse. A dark star is not guaranteed to follow one identical ending. Rotation, accretion, dark matter heating, and the amount of helium already produced can all change the route. For the most massive and weakly supported cases, collapse continues. The central region falls inward faster. Matter that once adjusted through hydrostatic equilibrium begins moving on a dynamical timescale, set mainly by the density of the star and the strength of gravity. A process that may have taken millions of years to prepare can become much faster once equilibrium is lost. That contrast is common in astronomy. A cloud can gather slowly and then form a star quickly. A massive star can burn for millions of years and then collapse in seconds. The universe often spends a very long time arranging the furniture before removing the floor. As the center contracts, temperatures can become high enough to create large numbers of neutrinos. These particles escape easily and carry energy away, which reduces the pressure available to resist gravity. Photons are trapped because they interact frequently with the dense matter. They cannot transport energy outward quickly enough to stop the infall. The center continues becoming smaller, denser, and more strongly curved. At some stage, an event horizon forms. This is not a solid surface appearing inside the star, it is a boundary in space-time. Once matter or light crosses it, every possible future path leads farther inward rather than back out to the surrounding universe. From then on, the central object is a black hole. The phrase black hole forms can make the event sound as though a dark sphere has been inserted into the middle of the star. A better description is that the collapsing matter creates a region from which outward escape is no longer possible. The event horizon grows as additional material falls through it. Gas outside may still be moving, rotating, colliding, and radiating. The black hole begins inside an active collapse rather than arriving as a finished object with a tidy border. If the star were perfectly spherical and had no rotation, much of the material could fall inward with relatively little left outside. Real stars are unlikely to be that obliging. The gas that built the dark star carried angular momentum, and the star itself may have been rotating. As the object contracts, rotation speeds up, just as a skater spins faster after drawing in their arms. Material near the equator may then have too much angular momentum to fall directly through the new horizon. That material can form a disk around the black hole. Friction, magnetic stresses, turbulence, and gravitational forces move angular momentum outward through the disk, allowing some gas to spiral inward. As it descends into the black hole's gravitational field, it heats and can become extremely bright. The black hole itself emits no light from inside the horizon, but the material around it can produce more radiation than a galaxy full of ordinary stars. This distinction will matter whenever we compare black holes with dark stars. A dark star has a photosphere. Radiation works its way through the stellar interior and leaves from an extended gaseous surface. A black hole has an event horizon and no material surface. The light associated with it comes from gas outside the horizon, usually in an accretion disk, a hot corona shocks or jets. Both objects can therefore appear luminous, but they are not shining in the same way. The dark star converts dark matter annihilation energy into heat distributed through a large body of hydrogen and helium. An accreting black hole converts the gravitational energy of falling material into heat and radiation in a much smaller region. One glows because of what happens throughout a star. The other appears bright because matter is being heated before it disappears beyond a horizon. The collapse may preserve a large fraction of the original stellar mass in the black hole, although the exact fraction depends on rotation and the violence of the event. Some material can remain in a disk, some may be expelled through winds, shocks, or jets. Neutrinos and gravitational waves carry away energy. A rotating collapse can be less tidy than a nearly spherical one, which is not surprising. Rotation is astronomy's preferred method for turning a simple diagram into several years of simulation work. If a dark star has reached 100,000 solar masses before collapse, even a substantial loss can leave a very heavy black hole seed. If it has reached 1 million solar masses, the remnant may begin in the range normally called supermassive, or very close to it. The word seed does not mean the black hole is small. It means that it is an initial object from which a still larger black hole can grow. This gives the dark star idea one of its main cosmological attractions. Quasars powered by massive black holes existed when the universe was still young. Starting from a black hole of 10 or 100 solar masses requires a long period of efficient accretion to reach hundreds of millions or billions of solar masses. Starting from a remnant of 100,000 solar masses removes several stages from the calculation. Black hole growth is not unlimited. Gas falling toward the hole becomes hot and luminous, and that radiation pushes against later gas trying to enter. The familiar Eddington balance returns in a new setting. If accretion remains near the Eddington rate, the black hole can grow exponentially, but each multiplication of its mass takes time. Interruptions, gas shortages, mergers and feedback all alter the schedule. A heavy seed is therefore helpful rather than magical. It does not instantly explain every early quasar. The host halo must supply gas. That gas must lose angular momentum. Radiation must escape without stopping the inflow completely. The black hole may merge with other black holes, or it may be displaced by gravitational interactions. The route from a collapsed dark star to a billion solar mass quasar still contains enough uncertainty to keep several research groups occupied. The dark star route is also not the only proposed way to make a heavy seed. A large primordial gas cloud might collapse directly without first spending a long period as a dark matter-powered star. A dense stellar cluster might undergo repeated collisions and build a massive object. Smaller black holes might accrete unusually quickly. Primordial black holes have also been discussed, although their existence and permitted abundance are tightly constrained. The early universe has several applications for the same position, and the interview process is ongoing. A supermassive dark star would differ from the usual direct collapse picture in its earlier history. It would have spent time as an extended luminous stellar object supported by dark matter heating. It could continue accreting because its surface stayed relatively cool. When that support failed or relativistic instability took control, it would collapse from a mass already suitable for a heavy black hole seed. The remnant may inherit more than mass. It can inherit angular momentum from the star and the accretion flow. A spinning black hole changes the innermost stable orbits of the surrounding disk and can affect how efficiently accretion releases energy. Magnetic fields wound up in the disk may help launch jets along the rotation axis. These jets can carry energy far beyond the central system and alter gas throughout the host halo. None of this means every dark star collapse would produce a visible quasar immediately. A black hole needs fuel outside the horizon to shine. If feedback from the contracting star has already cleared the surrounding gas, the new hole could be comparatively quiet. If a dense envelope or disk remains, accretion could begin rapidly and create a bright source. The difference between a quiet black hole and an active one is not a difference in the black hole itself, so much as a difference in its surroundings. The same mass can be difficult to notice in one environment and impossible to ignore in another. A black hole without nearby gas is almost entirely a gravitational presence. Give it a dense meal, and it becomes one of the brightest engines in the universe. This is where the cosmic imposters enter. When astronomers observe an extremely distant source, they rarely receive a clear image of its internal structure. The object may appear as a few pixels or as a point of light. Its radiation has travelled for billions of years, been stretched by cosmic expansion, absorbed at selected wavelengths by intervening gas, and collected one photon at a time by a telescope. Several very different sources can then produce broadly similar measurements. A single supermassive dark star may be bright enough to resemble a small young galaxy. A compact cluster of ordinary population 3 stars can combine its light into one unresolved source. An accreting black hole can contribute ultraviolet and visible radiation that looks like unusually efficient star formation. A galaxy containing both stars and an active nucleus can imitate parts of all three. The problem becomes harder because brightness alone does not reveal size. An object may be intrinsically powerful or merely magnified by gravitational lensing. A foreground galaxy cluster can bend space-time and amplify light from a source behind it. That helps telescopes detect objects that would otherwise be too faint, but it also means the observed brightness must be corrected using a lens model. A small error in magnification becomes a larger error in the inferred mass or luminosity. Apparent compactness is also ambiguous. A source that looks point-like may truly be one star, but it may instead be a galaxy too small or too distant for the telescope to resolve. An active galactic nucleus can dominate the central light of a larger host, making the system look more compact. The fact that something resembles a point does not prove it has only one point's worth of complications. Colour provides more information, but not a unique answer. Astronomers measure brightness through several filters and build a spectral energy distribution, showing how the detected energy changes with wavelength. A dark star model predicts a spectrum based on its surface temperature, gravity, atmosphere, and redshift. A young galaxy model combines the light of many stars, nebular emission from gas, and possibly dust. An active black hole adds radiation from an accretion disk and surrounding material. With only a few broad filters, different models can fit the same data. A cooler dark star at one mass may reproduce colours similar to those of a young low metallicity galaxy. A black hole hidden inside a galaxy may add just enough central light to make the galaxy appear too bright for its estimated stellar mass. Adjust the age, dust content, star formation history, or lensing magnification, and the interpretation changes again. Spectroscopy is more useful because it spreads the light into many wavelengths and reveals individual features. Atoms and ions absorb or emit radiation at specific energies. The pattern of hydrogen and helium lines can constrain temperature, composition, density, and the source of ionization. Line widths reveal motion. Very broad lines can indicate gas moving rapidly near a black hole. Narrower nebular lines may come from a surrounding star-forming region. A dark star made from nearly primordial gas should not display the rich set of metal lines expected from a chemically evolved galaxy. That sounds decisive, but a very young galaxy can also be extremely metal-poor. The absence of obvious metals may mean one unusual star, a cluster of first stars, or a galaxy observed before much chemical enrichment. Lack of evidence is useful, but it does not always choose a single suspect. Helium can provide stronger clues. Some dark star atmosphere models predict helium absorption features, including a feature associated with singly ionized helium, under particular temperature and surface gravity conditions. A surrounding nebula powered by very hot stars or an accreting black hole may instead produce helium in emission. The distinction between absorption and emission, together with the overall spectrum, could help separate an extended stellar photosphere from ionized gas around a harder source. Even that test requires caution. Gas between the source and the telescope can alter the spectrum. The dark star may have an accretion envelope that adds emission. A galaxy can contain both stellar absorption and nebular emission. A black hole can be obscured, changing its apparent continuum. Strong evidence will probably come from several features agreeing at once rather than one line behaving perfectly. Variability offers another possible clue. Accretion disks around black holes can change in brightness as the inflow fluctuates. The innermost emitting region is compact, so some changes can occur relatively quickly when measured in the source's own frame. A supermassive dark star is much larger, and changes across its surface cannot coordinate faster than signals can travel through the object. Its total output may therefore be steadier over short timescales. Distance complicates this test because cosmic expansion stretches observed time intervals. A change taking 1 month near the source can appear to take many months to us at high redshift. Telescope surveys also revisit fields on irregular schedules. An apparently steady object may simply not have been watched often enough, which is a common difficulty in both astronomy and unattended cooking. X-rays can support a black hole interpretation because hot gas near an accreting black hole often produces them. A dark star photosphere at several thousand or tens of thousands of Kelvin would not be expected to create the same strong, hard X-ray source. Yet the absence of detected X-rays does not rule out a black hole. The source may be faint, heavily obscured, or so distant that the available observations are not sensitive enough. Radio emission and jets can also indicate accretion onto a black hole, but many active nuclei are radio quiet. A non-detection again narrows the possibilities without ending the discussion. The earliest objects are observed near the limits of current instruments, where silence may reflect the telescope rather than the source. The surrounding environment adds another layer. A lone dark star could sit in a small halo with little extended starlight. A galaxy should contain additional stars and gas, although they may be too faint to resolve. An active black hole may ionize a larger region or produce characteristic ratios among emission lines. Measuring those properties requires deeper observations than simply detecting the object. This is why astronomers use the word candidate. A candidate is an object whose measured properties are consistent with an interpretation worth testing. It is not a confirmed example, waiting only for a more enthusiastic caption. Several distant sources observed with the James Webb Space Telescope have been compared with supermassive dark star models, and later work has examined available spectra. The same sources can also be interpreted as galaxies, and active black holes remain part of the wider debate over unexpectedly luminous early objects. A secure identification would need to make the alternatives increasingly uncomfortable. The source should have the luminosity and temperature expected for a dark star. Its spectrum should be consistent with a nearly primordial atmosphere. The inferred radius and surface gravity should make sense for one extended object. Features associated with a hot accretion disk, broadline region, mature stellar population, or enriched interstellar gas should be absent or convincingly weak. Confirmation would also have consequences beyond naming a new type of star. It would show that dark matter can interact or annihilate in a way capable of heating ordinary gas. It would provide information about particle mass, annihilation rate, and perhaps scattering. It would reveal a new route through the first stages of stellar evolution and offer a mechanism for creating heavy black hole seeds. A confirmed accreting black hole at the same distance would be important for a different reason. It would show that massive black hole growth was already underway. A compact galaxy would teach us about unexpectedly rapid star formation. A cluster of population 3 stars would provide the first direct view of the stellar generation that enriched the universe. The imposters are not disappointing alternatives. Every suspect is scientifically interesting. The difficulty is that the universe does not arrange them in separate labeled display cases. A dark star can become a black hole. A black hole can sit inside a galaxy. A galaxy can contain a dense star cluster. Their light can overlap, and the object can change between categories during the time represented by different observations. The dark star may therefore be both a source and a stage. During its inflated life, it resembles a cool, extremely luminous star. During contraction, it becomes hotter and begins ionizing its surroundings. During collapse, much of its mass can disappear behind an event horizon. Soon afterward, the remaining disk may turn the new black hole into a bright accreting source. One history can produce several different appearances without moving to a different part of the sky. By the time its light reaches us, we see only one interval from that history. The task is to decide whether the photons left an extended stellar surface, a compact accretion disk, a collection of ordinary stars, or a mixture of them. That decision depends on extracting more detail from very faint light and comparing it with models that are honest about what they do not yet know. The black hole at the end of the process may eventually become far larger than its parent star was at collapse, drawing in gas and merging with other holes as galaxies assemble around it. But before following that later growth, the next practical question is not what a dark star might become, but how a telescope could detect one before it transforms into something else. Finding one begins with accepting that we probably will not see it as a star. That sounds like an inconvenient start to a search for stars, but distance changes what a telescope can reveal. A dark star forming in the early universe could be hundreds, thousands, or even 1,000,000 times more massive than the Sun, with a surface extending across several astronomical units. Up close, that would be enormous. Seen from more than 13 billion light-years away, it could still occupy less than a single resolvable point in an astronomical image. The telescope collects light. From that light, astronomers have to work backward. They measure how bright the source appears. They divide the light into different wavelengths. They look for absorption and emission features. They estimate how far the radiation has travelled, how much cosmic expansion has stretched it, whether intervening material has absorbed some of it, and whether a foreground object has magnified it through gravitational lensing. Only after all of that can they ask what produced the photons in the first place. This is less like photographing a mysterious animal, and more like finding 3 hairs, 1 footprint and a slightly damaged sandwich, then trying to decide what walked through the campsite. The first clue is distance. Dark stars are expected to belong mainly to the early universe, so astronomers search at very high redshift. Redshift measures how strongly the wavelength of light has been stretched while travelling through expanding space. A photon emitted in the ultraviolet when the universe was young may reach us today in the infrared. The larger the redshift, the greater the stretching, and generally the farther back in cosmic history we are looking. The letter used is simply Z. An object at a redshift of 11, 12, 13 or 14 is not merely distant in the everyday meaning of the word. We are receiving light that left when the universe was only a small fraction of its present age. This creates a useful feature of astronomy that would be deeply inconvenient in most other professions. Looking farther away means looking further into the past. You cannot point a telescope toward an ancient galaxy and see what it is doing tonight. You see what it was doing when the light left it. If that journey lasted more than 13 billion years, the object may have changed beyond recognition or disappeared entirely by the time its photons reach our instruments. A dark star could have grown, exhausted its dark matter supply, contracted, collapsed into a black hole, and helped build an early galaxy while its earlier light was still travelling toward Earth. The telescope sees the old version. For decades, this extreme distance made the search largely theoretical. Astronomers could calculate what dark stars might look like and estimate whether future telescopes could detect them, but the necessary observations sat near or beyond the limits of available instruments. Then the James Webb Space Telescope began observing the infrared universe with enough sensitivity to reveal surprisingly bright objects from the first few 100 million years of cosmic history. Webb is particularly useful because the light from those early objects has been redshifted into the wavelengths its instruments were designed to study. Its near-infrared camera, or NIR-CAM, can photograph very faint distant sources through a collection of filters. Instead of measuring one total brightness, astronomers measure how much light arrives in several wavelength ranges. The result is a rough outline of the source's spectrum. Imagine looking at a lamp through a sequence of coloured windows. Behind one window, it appears bright. Behind another, it becomes dim. Through a third, it may nearly disappear. Those differences tell you something about the lamp and about anything between you and it. NIR-CAM does something much more precise, and thankfully without anyone carrying a telescope-sized box of coloured windows around the observatory. One of the most important patterns in a very distant object is a sudden drop in light at particular wavelengths. Neutral hydrogen between us and the source absorbs radiation shorter than a characteristic wavelength associated with hydrogen. Because cosmic expansion shifts that boundary toward the infrared, astronomers can estimate the source's redshift by determining where the drop appears across the filters. This method gives what is called a photometric redshift. Photometric redshifts are extremely useful because cameras can observe many objects at once. A deep image may contain thousands of faint galaxies. Astronomers can identify which ones have colours consistent with very high redshift and select the most interesting targets for closer examination. But photometry has limitations. Different kinds of objects can produce similar colours. A nearby dusty galaxy can sometimes resemble a much more distant source. Strong emission lines can make one filter unusually bright and confuse a simple interpretation. A combination of stellar age, dust, chemical composition, and redshift can imitate another combination. That means the first stage of a dark star search is not usually, there it is. It is more like, that is strange enough to deserve another night of telescope time. Researchers can take theoretical dark star models and calculate how those stars would appear through Webb's filters at different redshifts. They can change the stellar mass, temperature, dark matter assumptions, and atmosphere. Cosmic redshift is then applied to the predicted spectrum, producing synthetic measurements that can be compared with real observations. If a source matches one of those models, it becomes interesting. It does not become proven. This distinction became especially important after Webb's first deep observations of extremely distant objects. Several surprisingly luminous sources were identified in the JADES survey, the JWST Advanced Deep Extragalactic Survey. Researchers studying supermassive dark stars compared some of those sources with dark star atmosphere models, and found that several could be fitted by individual supermassive dark stars. The earliest widely discussed examples included objects known as JADES-GS-Z11-0, JADES-GS-Z12-0, and JADES-GS-Z13-0. Those names are not particularly romantic, but astronomy has discovered enough objects that names such as Gerald and Susan would eventually create administrative difficulties. The important part is that their measured infrared brightnesses and colours could be reproduced by models of very massive dark stars at high redshift. A single supermassive dark star can be exceptionally luminous. An object approaching 1 million solar masses may produce as much light as a small galaxy. If the source is too distant for Webb to resolve its physical size, one enormous star and a compact collection of many ordinary stars can therefore appear frustratingly similar. This is one of the central observational challenges. Suppose Webb detects a point of light in the young universe. Its luminosity appears enormous. One explanation is a dark star with hundreds of thousands of solar masses. Another is a small galaxy containing millions of ordinary stars. A third is a galaxy with a feeding black hole in its centre. A fourth is some combination of stars, gas, and a black hole. A photograph alone may not tell them apart. Astronomers next examine morphology, meaning the shape and apparent extent of the source. A genuine, isolated dark star should be extremely compact on galactic scales. At those distances, it would usually appear unresolved, meaning Webb could not distinguish its physical surface from a point source. A galaxy may look slightly extended if it is large enough, and the observations are sharp enough. Unfortunately, early galaxies can also be extremely compact. Some are so small that separating them from unresolved objects pushes against the limits of Webb's imaging resolution. A central bright source can dominate a faint surrounding galaxy. Gravitational lensing can stretch the image. Noise can alter the measured profile. The difference between one object and many objects packed into an inconveniently small region is not always obvious. So astronomers turn to spectroscopy. Webb's near-infrared spectrograph, or NIR spec, takes incoming light and spreads it across wavelengths. Instead of several broad measurements from camera filters, researchers obtain a much more detailed spectrum containing peaks, dips, edges, and slopes. Those features are the fingerprints of matter interacting with radiation. Hydrogen absorbs light at particular wavelengths. Helium has its own set of transitions. Oxygen, carbon, nitrogen, neon, and other elements contribute additional features. Hot ionized gas can produce bright emission lines. A stellar atmosphere can create absorption lines when cooler material above the photosphere removes specific wavelengths from the outgoing radiation. A spectrum therefore begins to tell us what the source contains and how that material is behaving. For a simple primordial dark star, the expectation is mainly hydrogen and helium. The object forms before generations of stars have enriched its gas with substantial amounts of heavier elements. Finding strong signatures of oxygen, carbon, or other metals associated directly with the stellar atmosphere would make the simplest pristine dark star model difficult to maintain. The word directly is important. A dark star could exist in an environment containing other objects. Gas nearby might have been enriched by an earlier supernova. A neighbouring stellar population could add metal emission lines to the combined spectrum. An unresolved source might contain a dark star inside a more complicated system. Once we allow all of those possibilities, however, interpretation becomes harder. Every additional component can explain another feature, but it also moves us away from the clean prediction of one isolated primordial star. Scientists prefer models that explain the evidence without requiring an increasingly busy collection of invisible roommates. One proposed spectral clue for dark stars involves helium. Atmosphere calculations for some supermassive dark star models predict an absorption feature from singly ionized helium at a rest wavelength of about 1640 angstroms. Astronomers usually write it as He21640. The distinction between absorption and emission matters. Very hot population 3 stars can ionize helium in the gas surrounding them. When that gas recombines and releases energy, it may produce He21640 in emission. Active black holes can also generate hard radiation capable of producing helium emission. A dark star with the appropriate atmosphere could instead show the feature in absorption. In a spectrum, emission appears as extra light at the characteristic wavelength. Absorption appears as missing light. You can think of emission as someone adding a note to a musical recording and absorption as someone carefully removing one. The final sound may still contain the same basic tune, but the direction of the change tells you something about what happened. In 2025, researchers examining available NIR spec data reported that several jade sources were spectroscopically consistent with supermassive dark star models. They also reported a tentative He2 1640 absorption-like feature in Jade's GS-Z14-0. Tentative is the important word. The signal was weak, and weak features in extremely faint sources must be treated cautiously. Noise can produce dips. Calibration uncertainties can alter them. Additional observations can make a promising feature stronger, weaker, or vanish entirely. This is normal science rather than a problem unique to dark stars. The first hint of something interesting often arrives at the exact strength needed to make everyone argue about it for another year. JADES-GS-Z14- also demonstrates why identification is complicated. Observations at other wavelengths have indicated oxygen in its environment. Oxygen was not produced in significant quantities during the Big Bang. It must be made inside stars and later released. A clean, isolated, pristine dark star should not be surrounded by an obviously metal-enriched environment. That does not mathematically forbid a dark star from being present. It could mean the object exists alongside enriched gas or other stars. But the simple explanation of one untouched primordial dark star becomes less attractive. A conventional galaxy interpretation remains entirely serious. This is exactly how candidate searches should work. A model explains some observations, new data test it, and any conflicting evidence forces the model either to become more detailed or to lose ground. No one earns additional scientific points for remaining loyal to the first interpretation. Researchers have continued developing ways to search larger web datasets for dark star-like sources. Instead of comparing every distant object manually with a catalogue of theoretical spectra, computational methods can identify sources whose colours or spectra resemble the predictions. Machine learning approaches have even been trained on synthetic dark star observations. The computer is shown many examples generated from models and learns patterns that separate them from other possibilities. It can then scan observational catalogues and identify targets worth examining more carefully. This does not allow artificial intelligence to discover a dark star simply by feeling confident about one. The algorithm is only as useful as its training data and assumptions. If the theoretical spectra are incomplete, the classifications inherit those limitations. If the comparison sample does not contain the right kind of galaxy or active black hole, the system may confidently label an imposter. Machine learning can make the search faster. It cannot remove the need for evidence. Astronomers also use gravitational lensing to push the search toward objects that would otherwise be too faint. Massive galaxies and galaxy clusters bend space-time around themselves. Light from a distant source passing through that curved region can be redirected and magnified. The foreground mass acts as a natural telescope. Sometimes it produces multiple images of the same background object. Sometimes it stretches a galaxy into an arc. Sometimes the main effect is simply to make a tiny distant source brighter. For dark star searches, magnification could reveal objects less massive than the extreme, supermassive versions detectable without help. A star that is normally just below Webb's sensitivity might become observable if a foreground cluster happens to magnify it strongly enough. The difficulty is that lensing magnification must then be estimated accurately. If an object appears 100 times brighter because of lensing, its intrinsic luminosity is 100 times lower than the raw observation suggests. The inferred dark star mass changes accordingly. Different models of the foreground cluster can predict slightly different magnifications, especially near regions where lensing becomes very strong. Nature has kindly provided a free telescope and neglected to include the calibration manual. There is another possible method based on numbers. If dark stars existed, theoretical models predict some abundance depending on how frequently suitable dark matter halos formed and how long the stars survived. A long-lived luminous population could contribute noticeable numbers of compact objects at particular redshifts. If surveys find far fewer candidates than predicted, certain versions of the model can be constrained. This approach requires caution because the predicted population depends on uncertain formation efficiency. Not every early halo necessarily creates a dark star. Some may fragment, some may fail to concentrate dark matter sufficiently. Some dark stars may exhaust their fuel quickly. Others may grow for millions of years. Counting objects becomes meaningful only after those uncertainties are included. The search also benefits from studying objects that do not look like dark stars. Ordinary high redshift galaxies teach astronomers how compact early galaxies can be. Population 3 models predict what metal-free stellar populations should contribute. Observations of active galactic nuclei reveal how black holes behave at early times. Every alternative becomes a reference against which the dark star interpretation must compete. This comparison is essential because a convincing discovery cannot merely fit the dark star model. It must fit better than the alternatives. Suppose a distant source has the correct overall colour for a dark star. Good. Can a young galaxy reproduce it? Suppose it is unresolved. Useful. Could a compact galaxy remain unresolved at the same distance? Suppose it lacks obvious metal lines. Interesting. Could an extremely metal-poor stellar population do the same? Suppose He2 appears in absorption. More interesting. Is the feature statistically secure? Could stellar atmospheres surrounding gas or instrumental effects reproduce it? Each answer removes part of the uncertainty. The strongest case would combine several independent clues. The source would be extremely luminous but remain unresolved. Its spectral shape would correspond to the temperature expected for a dark star of plausible mass. its atmosphere would appear dominated by hydrogen and helium. The inferred surface gravity would fit an extended stellar object. A characteristic helium absorption feature might be present. Strong signatures of an accreting black hole would be absent. Extended galactic starlight would remain weak or undetected. Even then, repeated observations would matter. A faint spectral line that appears once needs confirmation. A suspected point source should remain point-like in deeper imaging. Different instruments should agree on the brightness. Independent teams should be able to model the data without requiring the same assumptions. That process can seem slow compared with a headline announcing that someone may have found a star powered by dark matter. Slow is useful. Dark matter has resisted direct identification for decades. A confirmed dark star would affect particle physics, cosmology, stellar evolution, black hole formation, and our understanding of the first luminous objects. The standard of evidence should therefore be considerably higher than the dots looked promising. There is also the possibility that the search produces no confirmed dark stars. That would still teach us something. If Webb and future telescopes examine large numbers of suitable early objects, and none match robust dark star predictions, researchers can constrain how frequently the objects formed or how long they lived. Depending on the model, non-detection could limit combinations of dark matter particle mass, annihilation strength, scattering behavior, and halo conditions. Failure to find something is most informative when the theory clearly predicts where it should have been. This is one reason researchers calculate observability before searching. They estimate a dark star's luminosity at different masses. They redshift its spectrum. They apply the sensitivity limits of a telescope. They calculate how much cosmic volume a survey probes. From that, they estimate whether 0 detections, 1 detection or dozens would be surprising. A survey that had almost no chance of finding a dark star tells us little when it finds none. A survey that should have found hundreds and sees 0 creates a much more uncomfortable afternoon for the theory. Future observations may improve the search in several ways. Deeper Webb spectroscopy can strengthen or reject weak helium features. Longer exposures can reveal faint emission from surrounding galaxies. Repeated imaging can test variability. Measurements at additional wavelengths can search for signs of black hole accretion, dust, or chemically enriched gas. Ground-based observatories will contribute as well. Extremely large telescopes equipped with adaptive optics and sensitive infrared spectrographs can study some high redshift sources in ways that complement space observations. Radio and sub-millimeter facilities can detect cool gas, dust, and atomic or ionic lines invisible to Webb. X-ray observatories can test whether a hidden accreting black hole is present. One telescope rarely receives the entire case. Webb may find the suspect. A radio telescope checks the surroundings. An X-ray observatory looks for an accretion engine. A future infrared telescope obtains a cleaner spectrum. Several years later, the collection of evidence becomes much more convincing than the original image. Astronomers have worked this way for generations. The instruments change. The photons become fainter. The spreadsheets become substantially larger. The basic principle remains the same. Dark stars add one more complication, because confirming one would also tell us something about matter that cannot be seen. Ordinary stars reveal their composition through their spectra, because the material producing their energy is also the material filling their interiors. Dark stars would be different. Their visible hydrogen and helium would not directly reveal the identity of the particles providing most of the heat. A spectrum might prove that the star has the structure expected from dark matter heating, without showing a dark matter particle itself. Researchers would then compare the observed mass, radius, temperature, luminosity, and lifetime with models using different particle properties. A lighter dark matter particle can produce a different annihilation heating rate than a heavier one. Different interaction strengths alter capture. Different halo densities affect how long the fuel lasts. The star becomes an indirect particle detector on an astronomical scale. Instead of building a laboratory several kilometers underground and waiting for one dark matter particle to strike a detector, nature may have placed an enormous hydrogen and helium object inside one of the densest dark matter environments in cosmic history. The laboratory is larger, the commute is worse, and the experiment began more than 13 billion years ago. There is something particularly useful about that early timing. The first star-forming halos existed when the average density of the universe was much greater than it is today. Their centers could contain dark matter concentrations difficult to reproduce around most modern stars. If annihilation heating ever had the opportunity to dominate stellar evolution, the first few 100 million years offered unusually favorable conditions. By observing those years directly, Webb is testing physics in an environment that no longer exists nearby. This is why apparently tiny smudges in deep field images receive so much attention. To the eye, one may look like a faint red pixel. Physically, its light may represent an entire young galaxy, a rapidly feeding black hole, a cluster of primordial stars, or perhaps one enormous dark star sustained by invisible particles. The image does not look dramatic enough for the possibilities contained inside it. That is normal. Some of astronomy's largest questions arrive as very small points on a screen. At present, the important word remains candidate. Several high redshift JWST sources have been shown to be consistent with supermassive dark star models, and spectroscopy has provided additional features worth testing. Other evidence makes simple dark star interpretations less secure for at least some of those objects. None of that gives us a universally accepted, confirmed dark star. The search has moved, however, from asking whether a telescope could ever see such an object to examining real sources that can be compared directly with the theory. That is a significant change. For years, dark stars occupied calculations describing an era beyond observational reach. Now astronomers can take an actual spectrum from an object that existed within a few 100 million years of the Big Bang and ask whether its light is compatible with a dark matter-powered star. The answer may eventually be yes, it may be no. It may turn out that dark stars formed but were smaller, shorter-lived, or less common than the most optimistic models predict. Perhaps some existed only briefly before fusion took over. Perhaps supermassive versions require conditions too rare to contribute much to cosmic history. Perhaps dark matter is the wrong kind of particle for annihilation heating to matter at all. Each possibility changes the interpretation, but none removes the value of asking the question. The search forces several fields of physics to meet in one observation. Cosmology determines the environment, gravity builds the halo, chemistry controls the primordial gas, stellar physics determines the structure, particle physics supplies the hypothetical fuel, general relativity influences the eventual collapse. Telescope engineering decides which photons finally reach a detector. Then a researcher receives a file containing a spectrum with a small dip in it. Much of modern astronomy is concealed inside moments like that. The next stage is not simply to collect more distant points of light. It is to decide what evidence would finally allow us to say that one of them is not merely consistent with a dark star, but actually requires something close to the dark star explanation. And that brings us back to the larger question we started with, because after following these objects from primordial gas to invisible heating, enormous growth, collapse, and the edge of detectability, we can finally ask what the term dark star is really telling us about the object itself, and what remains only a possibility written into the physics. The simplest answer is that a dark star would be a star made almost entirely from ordinary matter, whose early source of heat comes mainly from dark matter. That definition removes several misleading ideas immediately. It would not be a star made mostly from dark matter. It would not be a black hole. It would not be an ordinary star that somehow stopped producing light. And despite the name, it would not necessarily look dark. A dark star could be extremely bright. Its main ingredients would be hydrogen and helium, the same material expected in the first generation of stars. Gravity would hold that material together. gas pressure and radiation pressure would resist gravity. Energy would move through the interior and eventually escape from an extended photosphere. From the outside, much of its behavior would still look recognizably stellar. The unusual part would be the furnace. Instead of contracting until hydrogen fusion became the dominant source of energy, the forming object could receive enough heat from annihilating dark matter particles to slow that contraction. The added heat would increase the internal pressure, allowing the star to remain much larger and cooler at its surface than a normal massive primordial star. The one change affects almost everything that happens afterward. Because the star stays inflated, its centre remains cooler. Because its centre remains cooler, ordinary fusion is delayed. Because its surface remains relatively cool, it produces fewer hydrogen ionizing ultraviolet photons. Because those photons are less abundant, the star may have more difficulty driving away the gas falling toward it. Because the gas continues arriving, the star can grow. A small amount of invisible matter could therefore influence the final mass of an object made almost completely from visible matter. That is the basic dark star idea. It is easy to lose that simplicity after talking about WIMPs, accretion disks, gravitational contraction, helium lines, relativistic instability, and redshifts large enough to make an astronomer reach for a fresh notebook. Underneath all of those details is a competition between heating and cooling inside a forming star. Gravity tries to compress the gas. Press. Cooling allows the compression to continue. Dark matter annihilation adds heat. Pressure responds to the heat. If the heating becomes important soon enough, the object takes a different route through stellar evolution. The dark matter itself may represent a remarkably small fraction of the stellar mass. The overwhelming majority remains hydrogen and helium. That means a dark star is not the astronomical equivalent of a dark matter planet or a solid lump of some exotic substance. The invisible component acts primarily as an energy source. This is possible because annihilation can release a large amount of energy from a small amount of particle mass. If the relevant dark matter particles are their own antiparticles, two of them can meet and transform their mass into other particles and radiation. Some of those products escape, others interact with the ordinary gas and deposit their energy as heat. Once that heat has been absorbed, the star does not remember where it came from. The gas warms, pressure rises, photons are produced and transported outward. Eventually, ordinary light leaves the surface. Someone observing the star from a great distance would not see streams of dark matter moving through it. They would see radiation from hydrogen and helium, and would have to infer the hidden power source from the star's unusual structure. This is why the name can cause so much confusion. Dark describes the fuel, it does not describe the appearance. The phrase also does not mean that dark matter behaves like a normal fuel stored in the centre. There is no dark matter core equivalent to the hydrogen-burning core of the Sun. Dark matter particles would move through the stellar volume on gravitational orbits. The density would generally be greatest near the centre, making annihilations more common there, but the particles would remain an unusual population passing through the ordinary material rather than behaving as part of the stellar gas. The original supply could be concentrated as the primordial cloud collapsed inside its dark matter halo. Ordinary matter falling toward the centre deepens the gravitational potential, and dark matter orbits respond. The central density increases. If the particle properties are suitable, annihilation heating becomes strong enough to alter the collapse. Later, the star may gain additional dark matter through changes in the surrounding halo, or through capture, if passing particles occasionally scatter from atomic nuclei and lose enough energy to become gravitationally bound. Every part of that sentence contains an uncertainty. We do not yet know what dark matter particles are. We do not know whether they annihilate in the required way. We do not know whether their interactions with ordinary matter are strong enough for efficient capture. We do not know whether the first star-forming halos maintain the dark matter densities required by the models, and we do not know whether a forming star would remain close enough to the centre of its halo for the process to continue. Those uncertainties are not small details added around the edge of an otherwise confirmed object. They are central to the idea. Dark stars remain hypothetical. that does not mean they are arbitrary. The models use familiar equations of gravity, gas pressure, radiation transport, stellar structure, and particle interactions. Researchers can calculate what would happen if dark matter has certain properties, and if primordial gas collapses under certain conditions. Those calculations produce objects with specific masses, radii, temperatures, luminosities, and spectra. A hypothesis becomes scientifically useful when it produces consequences that can be tested. Dark stars do. The predicted objects are not simply ordinary stars with a new name attached. During the dark-powered phase, many models produce stars that are much more extended than conventional stars of the same mass. Their surface temperatures remain relatively low. Their luminosities can become enormous. Their ionizing output is reduced compared with hotter population 3 stars. Under favourable conditions, they can continue accreting gas and grow far beyond ordinary stellar masses. The most extreme theoretical versions become supermassive dark stars. Instead of containing tens or hundreds of solar masses, they may reach hundreds of thousands or even around 1 million solar masses in some models. That is an extraordinary mass for one star. 1 million suns packed into one object would normally make us expect a compact, intensely hot structure approaching serious gravitational difficulties. Dark matter heating changes the route by keeping the stellar envelope inflated while the mass accumulates. The object does not escape gravity. It postpones some of gravity's consequences. That distinction matters. A dark star is not protected indefinitely. Dark matter particles annihilate and disappear from the useful fuel supply. Orbits can be depleted. Capture may be inefficient. The surrounding gas reservoir can run out. The star can move away from the centre of the halo. Its host system can merge with another structure. Radiation, rotation, or fragmentation can interfere with further growth. Eventually, if the dark matter heating falls below the rate required to support the inflated configuration, the star contracts. The temperature rises. Fusion becomes important. The surface gets hotter. Ultraviolet output increases. Accretion becomes more difficult. At that point, the object begins leaving the state that made it a dark star. A lower mass example might proceed through a period resembling the life of a very massive population 3 star. A much larger object could become unstable and collapse into a black hole. If the dark star had already accumulated an enormous mass, the resulting black hole could begin its own life with a substantial head start. That possibility connects dark stars with one of the major questions raised by observations of the young universe. Very massive black holes appeared remarkably early in cosmic history. Astronomers have several possible ways of producing their initial seeds. Ordinary massive stars can collapse and form relatively light seeds. Dense clusters can build heavier objects through mergers. Large gas clouds may undergo direct collapse. Other possibilities have also been proposed. A supermassive dark star offers another route. Allow the star to grow while dark matter heating keeps it cool and extended. Let it accumulate tens of thousands or hundreds of thousands of solar masses. Remove the dark matter support. Allow relativistic instability and collapse to take over. A heavy black hole seed is left behind. That seed still has to grow. It still needs gas. It may still need mergers. Its own radiation can interfere with accretion. Nothing about the dark star route removes the remaining work. It simply changes the starting point. There may even be observational consequences after the stellar phase has ended. Recent theoretical work has explored whether collapsed supermassive dark stars could produce unusual black hole systems surrounded by large gaseous envelopes, potentially connecting the idea with some of the compact red sources now being studied in JWST observations. That remains a proposed interpretation rather than an established explanation, but it shows how the dark star hypothesis can influence more than the structure of the original star. The most direct test would still be much simpler in principle. Find one before it collapses. That is what makes the James Webb Space Telescope so important to this subject. For the first time, Astronomers can examine individual luminous sources from the period when dark stars might plausibly have existed. Their light has been travelling for more than 13 billion years. Cosmic expansion has stretched much of it into the infrared, exactly where Webb is particularly sensitive. Several distant JWST sources have now been compared with supermassive dark star models. Some can be fitted by those models. Spectra have provided additional clues. Researchers have searched for features such as helium absorption that might distinguish an extended stellar atmosphere from a young galaxy or an accreting black hole. More candidates have been identified using newer automated techniques. None of that currently gives us a confirmed dark star. A source being consistent with a model is not the same thing as the source requiring that model. This may be the most important scientific distinction in the entire story. Imagine hearing a noise downstairs during the night. It is consistent with a burglar. It is also consistent with the refrigerator changing temperature, a pipe moving, a cat objecting to a closed door, or something on a shelf finally obeying gravity after several months of consideration. Consistent with tells you that an explanation remains possible. It does not tell you that the explanation has won. The same rule applies to distant objects observed by Webb. A luminous unresolved source might be one dark star. It might be a compact galaxy. It might contain an accreting black hole. It might be a dense cluster of stars. Several components may be blended together. The job is to gather enough independent evidence that competing explanations stop working. A convincing dark star detection would ideally give astronomers more than an unusual brightness. Its overall spectrum would need to match an extended hydrogen and helium atmosphere at a plausible temperature. Its luminosity and inferred mass would need to make sense together. Its apparent size would need to remain compatible with a single compact object. Its spectral lines would need to differ from those expected from ordinary stellar populations or active black holes. Evidence for substantial chemical enrichment would need an explanation. Signs of a hot accretion disk would count against the simplest stellar model. Repeated observations would have to reproduce the critical features. If several independent clues all point in the same direction, the case becomes much stronger. And if they do not, the dark star interpretation should lose ground. That willingness to lose is part of what makes the hypothesis scientific. We began tonight with a name that sounds as though it belongs comfortably beside black holes, dark matter, dark energy, and the other parts of astronomy apparently designed to make switching off the bedroom lamp feel academically appropriate. But dark stars are different from all three. A black hole is defined by an event horizon. Dark matter is the unseen gravitating substance inferred from its effects on galaxies, clusters, gravitational lensing, and cosmic structure. Dark energy is the name given to whatever is responsible for the accelerated expansion of the universe in our current cosmological description. A dark star would be an ordinary matter object whose stellar evolution has been altered by dark matter heating. Those categories should not be blended together merely because astronomy was apparently short of adjectives. There is another historical use of the phrase dark star that can add to the confusion. Long before modern black hole theory, scientists considered objects so compact that their escape velocity might exceed the speed of light under the physics then available. Those were sometimes described as dark stars. That is not what we have been discussing. Our dark star belongs to modern particle cosmology and the problem of the first stars. Its darkness is in the engine. Its visible body is still hydrogen and helium. Its existence depends on the behaviour of dark matter. Perhaps the most interesting part of the idea is that it connects scales that normally seem unrelated. At the smallest scale, it depends on hypothetical particles. Those particles may be far smaller than an atomic nucleus, and individually almost impossible to detect. At a larger scale, their annihilations can affect a stellar core. That changes the radius and temperature of an entire star. The altered star changes the flow of gas through a dark matter halo. Its unusual growth can change the mass of the black hole left after collapse. That black hole may influence the formation of a galaxy. A particle interaction too small to see could therefore affect structures spanning thousands of light years. Whether nature actually used that route remains unanswered. That is one reason dark stars are valuable even before anyone finds one. They provide a way to ask whether dark matter can influence ordinary matter through more than gravity on astronomical scales. Most evidence for dark matter comes from gravity. Stars orbit galaxies too quickly for the visible mass alone. Galaxies and clusters move as though more matter is present than telescopes reveal. Gravitational lensing maps mass where little or no light appears. The cosmic microwave background and large-scale structure also point toward a substantial non-luminous matter component. All of this tells us that dark matter has gravity. It does not yet tell us exactly what the dark matter is. A confirmed dark star would give us another type of clue. If its structure required annihilation heating, dark matter would have demonstrated a particle property beyond simply possessing mass and producing gravity. The star would become evidence for how dark matter interacts with itself, and perhaps, if capture were involved, how it interacts with ordinary particles. One observation could connect astronomy with experiments being conducted in laboratories on Earth. There is no guarantee that this will happen. The dark matter may not consist of WIMPs. It may consist of particles that do not annihilate efficiently. It may have interactions too weak to influence primordial stars. The central dark matter distributions in real mini-halos may differ from the profiles used in the most optimistic models. Computer simulations may eventually show that fragmentation or stellar motion usually destroys the conditions required for prolonged dark star growth. Observations may find that every proposed candidate is explained more naturally as a galaxy or a black hole. If that happens, dark stars will still have served their purpose. A hypothesis does not fail science by being rejected. It fails only if it cannot be tested. If observations exclude dark stars under particular assumptions, those observations tell us something about dark matter and early star formation. Models can be narrowed. Certain particle properties become less plausible. Certain halo conditions can be ruled out. Sometimes learning that nature did not choose an interesting possibility is exactly how we discover what it did choose. For now, the most accurate answer to our question includes one word that science uses frequently, and headlines use less enthusiastically. Maybe. What is a dark star really? It is a theoretically possible first-generation star, made primarily of hydrogen and helium, whose early structure is supported mainly by heat from dark matter annihilation, rather than ordinary nuclear fusion. It could be large. It could be cool compared with other massive primordial stars. It could shine very brightly. It might grow to extraordinary masses. It might later become a massive black hole. And we do not yet know whether the universe ever made one. That last sentence does not weaken the story. It is the reason the story is still happening. Webb continues to observe the cosmic dawn. New spectra are collected. Candidate objects are reanalyzed. Competing explanations are tested. Dark matter experiments continue searching for evidence closer to home. Simulations become more detailed. Stellar models add physics that earlier calculations had to simplify. Somewhere in those results, the dark star idea will either become more convincing or more restricted. Perhaps one distant point will eventually produce a spectrum that fits an enormous primordial stellar atmosphere and stubbornly refuses to behave like a galaxy or an active black hole. Perhaps deeper observations will resolve it into a collection of ordinary stars. Perhaps a faint metal line will appear and make the simple model impossible. Perhaps the characteristic helium signature will emerge cleanly in several sources. We do not know yet, and that is a perfectly acceptable place for science to be. When we began, a dark star sounded like something that ought to be black, cold, and difficult to see. Instead, we found a proposed object that could be huge, warm enough to glow brightly, and capable of becoming one of the most luminous individual stars imaginable. We followed the gas that could form it during the cosmic dark ages. We watched dark matter gather around the collapsing primordial cloud. we saw how annihilation heating might interrupt the usual route toward fusion. We moved through an interior where a tiny invisible component could support an enormous quantity of hydrogen and helium. We watched the star expand, remain comparatively cool, and continue accreting. We allowed it to grow from an unusual protostar into something massive enough to challenge our normal idea of what the word star means. Then the fuel weakened. Gravity began winning back the ground it had temporarily lost. The star contracted. Fusion switched on. Radiation hardened. Accretion became more difficult. And in the most extreme versions, the entire structure collapsed into a heavy black hole seed. Now the surviving evidence is travelling toward us as very old infrared light. That light is what astronomers have to work with. No sample can be collected. No spacecraft can visit. No probe can be lowered through the atmosphere. We receive photons, we measure them carefully, and from those measurements, we try to reconstruct what happened when the universe was only a few 100 million years old. So, before you drift off tonight, you can return to the question from the beginning. When you first heard the words dark star, what did you imagine? Perhaps a black sphere, perhaps a dead sun, perhaps something that swallowed light. Now, the image is different. If dark stars existed, they were not stars that had gone dark. They were stars whose visible light may have been made possible by an invisible source of heat. And if one of those distant JWST points eventually turns out to be a genuine example, it would mean that we had found more than a new type of star. We would have found a place where dark matter did something measurable inside ordinary matter, changing how a star formed, how large it became, and possibly what kind of black hole it left behind. Until then, it remains one of those useful scientific possibilities sitting between calculation and discovery. Not confirmed, not ruled out, specific enough to test, strange enough to keep looking. If you have enjoyed following this long route through the early universe, you can leave a like and subscribe to Science for Sleep. And if you are still awake, let me know where you are listening from and what you pictured when you first saw the title. I suspect at least a few people expected something considerably darker. For now, there is nothing else you need to calculate, compare, or remember. The telescope can keep watching the ancient universe. The researchers can keep arguing politely over spectra. The dark matter can continue refusing to introduce itself properly, and you can get some rest. Sleep well, fellow traveller, wherever you are listening from tonight.